All right, I think we're back online. I'm going on a little bit early today. Sometimes my schedule, I just feel like I have a little bit more time and I can get back on a bit earlier. My whole philosophy to this is I'm going to try to put in as much time as I can, especially early on in the project, because I'd hate to not reach the goal that I've set for myself or not reach that end point just because I was, slacking off in the beginning. So where we're at, I'm working through lectures right now, so that's all you're going to see me doing today, unless I stop to do something very small. Trying to finish all the lectures. So these next 3 days are going to be a big burst of finishing the lectures. I've spoken before. I repeat myself a lot in this live stream because I'm imagining very few people are going to see most of it. But my whole point of doing the lectures like this is just that I want to see all the material so I can decide where to focus my time and energy. Now, there's a trade-off because the material is cumulative. So if you don't master foundational concepts, you could be building a tower on a shaky surface and it could fall over. Now, I kind of split the middle in this trade-off and decided to do the first 10 problem sets and then go on. Of course, if you find the material more difficult, it's better to go slower and do more feedback, more problem sets in between. The downside of this is that you're not necessarily going to be investing time where you're weakest. Now, my general feeling of doing this in other MIT classes has been that the problem sets in terms of the actual difficulty are usually, I would say, about an order of magnitude harder than understanding the classes. So that means that it is often possible to follow all the lectures from lecture 1 to the end with zero comprehension difficulties. And then you get to the problem sets and you're struggling. And so this is kind of what is happening, except I'm also struggling a little bit on some conceptual points. So I'm just trying to note those when I'm going through this right now. I haven't stopped to ponder over them too much because I don't want to go down a rabbit hole where I spend, 2 days trying to clarify some point that turns out to not be that important in the big scheme of things. So again, I want to see that big picture so I can see which things are important, which things are coming up again and again and again and again versus something that it's just going to be for one problem or just going to be for one particular issue, that it isn't going to have that kind of ramifications. So for instance, if you've been following this class or if you know something about quantum mechanics, you will know some core ideas come up again and again and again. Operators, superposition, commutation, these are all very, very key ideas. So I even have spent some time doing some Feynman techniques on those. On the other hand, some of the ideas, for instance, the classical collapse or the collapse of the classical hydrogen atom, if you assume it's just like a planet rotating around a proton, that was something that I didn't quite understand, but it hasn't had much relevance, of course, because that's not quantum mechanics. That's what would be if quantum mechanics wasn't true. So I'm going to keep listening to them now. I think I'm trying to think of what lecture I'm at. I think I just finished lecture 15. So that means we have another 9 left. I'm going to maybe get done 2.5 to 3 today. And then we're just going to kind of take stock. Right now, we're moving up to the 3-dimensional case. So for the entirety of what I've been doing so far until last lecture was just 1-dimensional problems. So imagining if the entire universe just was existing on a 1-dimensional line, which even then there's considerable complexity, considerable stuff going on. So you have a lot of interesting things happening, even in that 1-dimensional case. Now, of course, we have 3 axes to work with. So you have things like rotation, you have things like angular momentum, you have these kinds of things. And so that's introducing new ideas about quantum mechanics, about how physics works. So, excuse me, a little bit of allergies right now. If I have to turn around to blow my nose, I apologize doing that on camera. I'm trying to be polite here, but unfortunately, when you're studying for a couple hours at a time, it's hard to keep focusing sometimes when you have to blow your nose. Yeah, so we finished up to lecture 15. I'm going to start on lecture 16 now. Let me just get it prepared, and then I'll dive right into it. I'm just going to post the link here to the lectures that we're doing. So I'm just going to put it here, just because a couple people have been like coming in midway and being like, what the heck is going on? I don't understand any of this. And so I'm hoping that if I post these links, if you are interested, you can follow. Obviously, I don't expect everyone to follow every lecture I'm doing or understand everything I'm watching. I'm more trying to show at the higher level how I study these classes than making it the effort of you studying along with me. Because of course, if you wanted to learn these materials, you could just take them yourself. You could just follow this class on your own pace. So giving me a certain amount of space. All right. All right. Excuse me. Apologies. So let's get started with watching a new lecture. So I'm just going to open one here. I'm going to load the new lecture. Just scale it here and make sure it is set to live. I think this morning I made the mistake of not sending. The way this light stream works is I've got different scenes. So this scene, you can see me. I have my camera of me on my right. I've got my notebook camera here, and I've got I'm sharing one of the video windows I'm drawing here. And every time I switch scenes, so if you see me switch from this to just having the camera, just one camera, some other camera setup, I have to make sure I click this send to live when I'm doing it. And I think I forgot to do that this morning. So I think there was one whole class where maybe you just saw my face and you could hear him talking rapidly in the background, but you couldn't necessarily tell what was going on. So, oh, we're a little bit dull here. I think we'll be okay. I might take a break to sharpen all these pencils. One of the commenters in the morning video said, I always have, the pencils never get dull. It's because I have 4 of them, and I usually sharpen them before the session, but I forgot this time. All right. And you know, before I begin, I just got to say, this is exciting stuff. I know it can sometimes be challenging, and obviously, if you're watching this and you're watching me, you can tell I'm getting frustrated sometimes, and I find it difficult, and I'm like, what's going on? And especially doing the problem sets is very hard. And it's very easy in those short-term moments of frustration or short-term feelings of inadequacy, incompetence, this kind of thing. And I've been certainly feeling a lot of them throughout this class. It's very easy to lose that big picture. And the big picture is what we're after, which is what we were looking for in the beginning, which was to understand quantum mechanics, understand how reality really works. And so I often, when I'm thinking about motivation on my end, I like to step back, because it's very easy to get hung up on, I don't get this right now, I don't understand this, and let that frustration dominate your overall desire to do something. Because learning is often frustrating, and it's only when you see it in the big picture that you see, you know what, but at the end of this process, I'm going to understand something that was baffling to me before, or I'm going to understand something that very few other people understand. So let me just adjust the blinds here. I'm doing a lot of rambling right now, but oh, my blinds, they're not going down very easily. All right. Okay. So that should be all right. We're having a little bit of a wet day today here in Vancouver. But at the same time, the light conditions are always changing. So hopefully we'll be able to keep going now. All right.
Open courseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right. Welcome, everyone. Hi. So today we're going to pick up where we left off last time in our study of angular momentum and rotations in quantum mechanics. Before we get started, let me open up 4 questions, pragmatic and physics related. Yeah.
So when you're solving for the 3D harmonic oscillator,
yes.
Solve for the energy value function, the product of phi dash phi y phi z.
Yes.
So we get an except for an assumption that phi d is equal to phi sub n of x plus
Good. Good. So what we had was that we had the energy. We wanted to find energy on the 3D harmonic oscillator. And we want to find energy eigenfunctions and eigenvalues. The way we did this was by saying, look, the energy of the 3D harmonic oscillator, which I think is a function of x and px and y and py and z and pz, has this nice form that we can write it as the energy operator purely in terms of x.
Hey, Joe.
P squared x upon 2m plus m squared upon 2 x squared plus, so this is a single 1D harmonic oscillator energy operator in the x direction plus E 1D in the y direction plus harmonic oscillator energy 1D in the z direction. Yeah, so that was the first observation. And then we said that, look, given that this splits in this fashion, and write my wave function, my energy eigenfunction should say phi of x, y, and z, and in separated form as a product, phi x of x, phi y of y, and phi z of z. And we use this and deduced that in order for this to be an eigenfunction of the 3D harmonic oscillator, it must be true that phi x of x was itself an eigenfunction of the x harmonic oscillator equals with some energy epsilon, which I'll call epsilon sub x, phi sub x, and ditto for y and z. And if this is true, if phi sub x is an eigenfunction of the 1D harmonic oscillator, then this is an eigenfunction of the 3D harmonic oscillator. But we know what the eigenfunctions are of the harmonic oscillator. The eigenfunctions of the 1D harmonic oscillator, we gave a name. We call them phi sub n. Okay. So what we then said was, look, if this is an eigenfunction of the 1D harmonic oscillator in the x direction, then it must be it's labeled by an n. And if this one is in the y direction, it's labeled by an L. And if this one is in the z direction, it's labeled by a z. But on top of that, we know more. We know what these energy eigenvalues are. The energy eigenvalues corresponding to these guys are, if this is phi n, this is En. This is En from the 1D harmonic oscillator. And taking this, using the fact that they're 1D eigenfunctions, and plugging in the energy eigenvalue equation for the 3D harmonic oscillator, tells us that the energy eigenvalues for the 3D case are of the form E1D x plus E2D, or sorry, E1D in the y plus E1D in the z, which is equal to
One at a time. One at a time.
H bar omega times n plus L plus m, from each of them 1/2, so plus 3/2. Cool. That is your question? Excellent. Other questions? Yeah.
So, energy doesn't measure that we related, right?
Yeah.
Because
Indeed.
I could see across the right?
Yes.
It is. So we have a lake ladder. Is there limits to them?
Very good question. So this is what we're going to pick up. So let me rephrase this. This is really two questions. Question number one. Look, there should be a relationship between angular momentum and energy. But we're just talking about angular momentum. Why? Second question, look, we've got a ladder, but is the ladder infinite? So let me come back to the second question. That's going to be at the beginning of the lecture. On the first question, yes, angular momentum is going to play a role in calculating energy. But two quick things to note. First off, consider a system which is spherically symmetric, rotationally invariant.
Thanks,
that means
Björn.
that the energy doesn't depend on rotation. I rotate the system, I haven't changed the energy. So if the system is rotationally invariant, that's going to apply some constraints on the energy eigenvalues and how they depend on the angular momentum, as we discussed last time. Let me see that slightly differently. When we talk about the free particle, 1D free particle, we've talked about this one to death. Take the 1D free particle. We can write the energy eigenfunctions as momentum eigenfunctions because the momentum commutes with the energy. Right? And so the eigenfunctions of the energy operator, indeed, even the IKX they're playing with, they're eigenfunctions of the momentum operator as well. Similarly, when we talk about a 3D system, it's going to be useful in talking about the energy eigenvalues to know a basis of energy eigenfunctions, or sorry, eigenfunctions of the angular momentum operator. Knowing the angular momentum operator is going to allow us to write energy eigenfunctions in a natural way, the same way that knowing the momentum operator allows us to write energy eigenfunctions in a simple way in the 1D case. Does that make sense? We're going to have a glorified version of the Fourier theorem, where instead of summing over the IKXs, we're going to sum over angular momentum eigenfunctions. And those are called spherical harmonics, and they are the analog of Fourier expansion for the sphere. But you're right, we're going to have to understand how they interact with the energy, and that'll be the topic of the next lecture. We're going to finish up angular momentum today. Other questions? Okay, so from last time, these are the commutation relations which we partially derived in lecture and which you will be deriving in your problem set. It's a really good exercise. Commit these to memory. They're your friends. Key thing here to keep in mind, h bar has units of angular momentum, so this makes sense. Angular momentum, angular momentum, angular momentum, angular momentum. So when you see an h bar in the setting, its job in some sense is to make everything dimensionally sensible. Okay, so the important things here are that Lx and Ly do not commute, they commute to Lz. Can you have a state with definite angular momentum in the x direction and definite angular momentum in the y direction simultaneously? No, because of this commutation relation, would have to vanish. Can you have a state with definite, so this is say the x component of the angular momentum. Can you have a state with definite angular momentum in the x direction and total angular momentum squared? Yes. Okay, great. That's going to be important for us. So in order to construct the eigenfunctions, it turns out to be useful to construct these so-called raising and lowering operators, which are Lx plus Ly. They have a couple of nice properties. The first is, since these are built by Lx and Ly, both of which commute with L squared, the L plus minuses commute with L squared. So these guys commute, so acting with L plus doesn't change, if we have an eigenfunction of L squared, acting with L plus does not change its eigenvalue. Similarly, L plus commuting with LT gives us h bar L plus or L minus with a plus or minus up front. This is just like the raising and lowering, this is just like the raising and lowering operators for the harmonic oscillator, but instead of the energy, we have the angular momentum. So this is going to tell us that the angular momentum eigenvalues, the eigenvalues of LT, are shifted by plus or minus h bar when we raise or lower with L plus or L minus, just like the energy was shifted for the 1D harmonic oscillator. The energy was shifted plus h bar omega was shifted by h bar omega when we acted with a plus on an energy. Same thing. Okay, so our goal. So questions on the commutations before we get going. In some sense, we're going to just take advantage of these commutation relations and explore their consequences today. So our goal is going to be to build the eigenfunctions and eigenvalues of the angular momentum operators, and in particular, of the most angular momentum operators we can, we take some commuting observables, L squared and LZ. Now you might complain what YLZ, oops, I don't need to conjugate, I mean a set. You might say YLZ, y not LX, and if you call this the Z direction, then I will simply choose a new basis where this is called the X direction. So it makes no difference whatsoever, it's just a name. The reason that we're going to choose LZ is because it plays nicely, that coordinate system plays nicely with spherical coordinates, just a conventional choice of spherical coordinates, where theta equals 0 is the up axis. There's nothing deep about that. We could have taken any of these. Okay, so this is our goal, so let's get started. So first, so we know, because of these commutation relations, we know, in particular this one, we know that we can find common eigenfunctions of L squared and LZ. Let us call those common eigenfunctions by name, y sub Lm, where such that, so let these guys be the eigenfunctions, the common eigenfunctions of L squared and LZ, i.e. L squared YLM is equal to, well, first off, units, this has units of angular momentum squared, h bar squared. So I got rid of the units. And we want our eigenvalue, Lm, and I'm going to give a, because I know the answer, I'm going to give it to calling this a random dimensionless number, which would be the eigenvalue. I'm going to call it a very specific thing, L plus 1. This is a slightly grotesque thing to do, but it will make the algebra much easier. So, similarly, so that's what the little L is. The little L is labeling the eigenvalue of L squared, and the actual value of that eigenvalue, I'm just calling h bar squared L plus 1. That doesn't tell you anything interesting. This was already a real positive number, so, you know, this could have been any real positive number as well, between L. Okay, similarly, LZ, YLM, I want this to be an eigenfunction. This has units of angular momentum, so I'll put an h bar. Now we have a dimensionless coefficient YLM, and I'll simply call that M. So if you will, these are the definitions of the symbols M and L, little l. And YLM are just the names I'm giving to the angular momentum eigenvalues. All right?
So do we want to put something here for explaining why we have h bar? And this must be from dimensional analysis, but I'm a little confused. So we know the operator. So let's just, this is going to be 1 over 3/2 length squared. And then we've got a okay, I'm just going to put a little note here. I got to get faster with my dimensional analysis.
Eigenfunctions. Cool. So I haven't actually done anything. I just told you that these are the eigenfunctions. What we want to know is what properties do they have and what are the actual values of the eigenvalues. So the two key things to note are first, that L plus and minus leave the eigenvalue of L squared alone. So they leave L alone. Right? So this is the statement that L squared on L plus YLM is equal to L plus on L squared YLM is equal to h bar squared L plus 1. The eigenvalue of L squared YLM. L plus YLM. And so we have L plus YLM is just as much an eigenfunction of L squared as YLM was itself. We would say eigenvalue. 2. So that came from where are we? That came from this commutation relation. Okay. So similarly, L plus minus raise or lower M by 1. Okay. The way to see that is to do exactly the same computation. LZ on L plus, for example, YLM is equal to L plus. Now we can write the commutator. LZ LT with L plus, we already have, is plus H bar L plus. So this is equal to.
Let me just write this down. LZL plus YLM. So this M is not actually a mass. I gotta make that clear. That's this M. So we have, this is gonna be LZ plus
H bar L plus. And from this term, L plus LZ and YLM, LZ and YLM gives us H bar M plus H bar M L plus YLM. It's equal to, pulling this out, this is H bar times M plus 1 times L plus. H bar M plus 1 L plus.
ML.
Plus YLM. So L plus is raised the eigenvalue M by 1. This state, what we get by acting on YLM with a raising operator, is a thing with M greater by 1. And that gives me the commutation function. And if we've done the same thing with minus, if you go through the minus signs, it just gives us this. Okay. So, what does that tell us? What this tells us is we get a ladder of states. Let's look at what they look like. Each ladder, for a given value of L, if you raise with L plus and lower with L minus, you don't change L, but you do change N. So we get ladders that are labeled by L. So for example, if I have some value of L1, this is going to give me a value, this is going to give me some state. I can label by M. I can, we'll leave the sign. I can raise it to get M plus 1 by L plus, and I can lower it to get N minus 1 by L minus. Okay, so I get a tower. And if we have another value, a different value of L, I'll call it L2, we get another tower. You get M plus 1, M plus 2, dot dot, minus 1, dot dot. So we have separated towers with different value of L squared. And within each tower, we can raise and lower by L plus, skipping by 1. Okay, questions? So that was basically the end of the last lecture, said slightly differently. So now here's the question. So this was the question that the student asked right at the beginning. Is this tower infinite? Or does it end? So I posed to you the question, is the tower infinite or does it end? And why? Okay, so it's tempting to say infinite in one direction because so it's because there's no balance in the angular momentum. That's tempting.
But at the same time, when you accelerate your operator on L, the eigenvalue L squared remains the same. So that you can't raise the constant angular momentum above the actual.
Thank you, exactly. So here's the statement. Let me restate that. That's exactly right. So look, L squared is the eigenvalue of the total angular momentum. Roughly speaking, it's giving you precisely in the state YLM, it's telling you the expected value of the total angular momentum, L squared. That's some number, right? Now, if you act with L plus, you keep increasing the expected value of LZ. But if you keep increasing it, LZ will eventually get much larger than the square root of L squared. That probably isn't true, right? That sounds wrong. Right? That was the statement. Excellent. That's exactly right. So let's make that precise. So is the tower infinite? No, and probably not for precisely that reason. So let's make that precise. So here's the way we're going to do it. This is a useful trick in general. This will outlive angular momentum and be a useful trick throughout quantum mechanics for you. I used it in a paper once. So here's the nice observation. Suppose it's true that the tower ends. Just like for the raising and lowering operators for the harmonic oscillator in one dimension, that tells us that in order for the tower to end, the state must be 0 once we raise it, the last state. So YL, and I'll call this M plus, must be 0. There must be a max. Oh, sorry. Let me actually, before I walk through exactly this statement, so let me make first the no slightly more obvious and precise. So let's turn that argument into a precise statement. L squared is equal to, just from the definition, L squared plus Ly squared plus LT squared. Now let's take the expectation value in the state YLM of both sides of this equation. So on the left-hand side, we get H bar squared LL plus 1.
Hold on a sec. Let me write it down here.
And on the right-hand side, we get the expectation value of Lx squared plus the expectation value of Ly squared plus the expectation value of LZ squared. But we know what the expectation value of LZ squared is h bar squared m squared. But the expectation value of Lx squared and Ly squared are strictly positive, because this can be written as a sum over all possible eigenvalues of Lx squared, which is the square of the possible eigenvalues of Lx, times the probability distribution. That's a sum of positive, strictly positive. These are positive guys. So LL plus 1 is equal to positive plus h bar squared m squared. And in particular, that tells you that it's greater than or equal to h bar squared m squared. Right? I mean, maybe these are 0. Right? So the least it can be is, so the most m squared can possibly be is the square root of LL plus 1. Or most m can be. Okay? So m is bounded. There must be a maximum m, and there must be a minimum m, because this is squared. The sign doesn't matter. Ever cool with that? Okay, so let's do a precise argument. What are the values of m plus and m minus? What is the top value of that of each power? Probably it's going to depend on total L, right? So it's going to depend on total L. Let's check that. So here's the nice trick. Suppose we really do have a maximum m plus. That means that if I try to raise the state YL m plus, I should get the state 0, which is not, that ends the tower. So suppose this is true. In that case, in particular, here's the nice trick. L plus YLM, if we take its magnitude, if we take the magnitude of the state is 0. It's the 0 function. So what's its magnitude? 0. Okay, you might not think that's all that incredible.
All right.
It's an observation. Okay, but no, what?
So we're doing L plus Y.
This is. We know how to work with this. In particular, this is equal to. I should have done this. Is equal to. I'm not going to use the Hermitian adjoint and pull this over to the right hand side. The adjoint of L plus is L minus. So this gives us YLM, L minus, L plus. YLM. This also doesn't look like much of an improvement until you know. This one is definition of L plus and L minus. But what's L minus L plus? Well, L minus L plus, we're going to get an Lx squared. So YLM. We get an Lx squared plus an Ly squared. We're going to get the sign right, if I'm not careful. Plus, well, let's just do it. Okay, so we have L minus L plus. So we're going to get a Lx ILy minus I Ly Lx. So plus I, coming here, of Lx with Ly. Okay. Good. So that's progress, YLM. But it's still not progress because the natural operators with which to act on the YLMs are L squared and LT. So can we put this in the form of L squared and LT? Sure. This is L squared minus LZ squared. YLM. L squared minus LZ squared. And then this is I H bar LZ times I is minus H bar LZ, so minus H bar LZ. YLM. And this must be equal to 0. But this is equal to, from L squared, we get H bar squared, LL plus 1. From the LZ squared, we get minus M squared H bar squared. And from here, we get minus H bar M, so minus M H bar squared. Where notice the units worked out. And all of this was multiplying YLM, but YLM, if it's a properly normalized eigenstate, which is what we were assuming at the beginning, is just 1. So we get this times 1 is 0. Aha! And notice that in all of this, this was M plus. We were working here with the assumption that L plus annihilated this top state. And so grouping this together, this says, therefore, H bar squared times, pulling out a common H bar squared from all this, times L plus 1, minus M plus 1, is equal to 0. And this tells us that M plus is equal to L. And if you want to be strict, put a plus on There's a very useful trick. If you know something is 0 as a function, you know its norm is 0, and now you can use things like Hermitian adjoints. Very, very useful. Okay, questions about that? Yeah. Good. Okay, so where this came from was I was just literally taking L plus and L minus, plugging it, taking the definitions. So if I have L minus, L minus is, just to write it out explicitly, L minus is equal to Lx because the end are observables in solar formation, so they're self-adjoint, minus I Ly. So L minus L plus gives me an Lx Lx, it gives me an Lx I Ly, it gives me a minus I Ly Lx, and it gives me a minus I I, which is plus 1 Ly squared. Cool? Excellent. Let's see a series expression here. Okay. Good. Other questions? Yeah. This here. Okay, good. So here when I jumped this stuff here. So here what I said is, look, I've got this nice operator acting on y1. I know how each of these operators acts on y1. LZ gives me an 8 bar m. Minus 7 h squared. LZ squared, L squared. And then overall, that was just some number times y1, which I can pull out of the inner product. Cool? Yeah. Good. This up here plus that look, there was a maximum value of m, so m squared had to be less than or equal to this. There's a maximum value than the minimum value. Maybe they're different, I don't know. I'm just going to be ambiguous. I'm going to be open-minded about it. Yeah. Yeah, awesome observation. Exactly. Okay, so we were going to get there a little bit. So I like that. That's exactly right. So let me go through a couple more steps, and then I'll come back to that observation. And I promise I will say so. Okay. So if we go through exactly a similar argument, let's see what happens if we did L minus on YL and minus, just to walk through the logic. So if this were, you lower the lowest one, you get 0. Then we get the same story, L minus, When we take the adjoint, we get L plus, L minus. Okay. And L plus, L minus, what changes? The only thing that's going to change is that you get this commutator the other direction, and there are minus signs in various places. The upside of which is that n minus is equal to minus L. So this is quite parsimonious. It's symmetric. If you take z to minus z, if you switch the angular momentum, sign the angular momentum, you get the same thing back. That's satisfying, perhaps. But it's way more than that. This tells us a lot about the possible eigenvalues in the following way. Look back at our towers. In our towers, we have that the angular momentum is raised lower by L plus. So the LZ angular momentum is raised lower by L plus. L remains the same. But there's a maximum state now, which is plus L. And there's a minimum state in here, L1. Here there's a minimum state minus L1. Similarly, for the other tower, there's a minimum state minus L2 and a maximum state L2. So how big each tower is depends on the total angular momentum. That kind of makes sense, right? If you've got more angular momentum, you can only step LZ by 1. You've got more room to move with a large value than with a small value. Okay. So what does that tell us about the values of M? Notice that M spans the values from its minimal value minus L to L in integer steps, in unit steps. So if you think about M is L plus is L, then M is L minus 1. If I keep lowering, I get down to M is minus L plus 1, and then M is equal to minus L. Okay. So the difference in the LZ eigenvalue between these guys, the difference is 2L. But the number of unit steps in here is 1 0, because 1 2L minus 1. So this is some integer, which is the number of states minus 1. So if these are n states, and I'll call this n sub L states, then this difference, twice L, is n sub L minus 1, because it's unit steps. Cool? So for example, if there were 2 states, so n is 2, 2L is equal to, well, that's 1, which is 2 minus 1. The number of states minus 1 also minus 1, so L is 1/2. Okay. And more generally, we find that L must be, in order for this process to make sense, in order for the n plus and the n minus to match up, plus 2, we need that L is of the form of an integer, n sub L minus 1 upon 2. Okay. So this tells us that where NL is an integer. NL is just the number of states in this tower. And it's a positive, strictly positive integer. If you have 0 states in the tower, then that's not very interesting. So this tells us that L is an integer or a half integer, but nothing else. Cool? So in particular, if it's an integer, if it's a half integer, that means 1/2, 3 halves, 5 halves. If it's an integer, it can be 0. So it runs being 0, but then 1. Okay, so that means we can plot our system in the following way. If we have L equals 0, yes. So if we have L equals 0, how many states do we have? If little L is 0, how many states are there? What's the largest value of LZ? So first of all, so good. What's the largest value of LZ, or of M, if little L is equal to 0? 0, because it goes from plus 0 to minus 0, so that's pretty much 0. So we have a single state with M equals 0 and L equals 0. If L is equal to what's the next possible value, 1/2, then M can be either 1/2 or we lower it by 1, which is minus 1/2. So there are 2 states. M equals 1/2 and M equals minus 1/2. So there's one tower. It's a very short tower. This is the shortest possible tower. Then we also have the state L equals 1, which has M equals 0. It has M equals 1, and it has M equals minus 1. And that's it. and so on and so forth. Four states for n equals, for L equals 3 halves, with states 3 halves.
Let me just write this down here. This would be 3 halves.
N equals 1 half, n equals minus 1 half, and minus 3 halves. Okay. The values of them stand from minus L to L with integer steps. Minus L to L with integer steps. And this is possible for all values of L that are at L, which are the form integer plus, well, all integer or half integer L's. Okay. So for every different value of the total angular momentum, the total amount of angular momentum you have, if you had a tower of states labeled by L's eigenvalue in this fashion. Questions? Does anyone notice anything troubling about these? Something physically a little discomforting about any of these? What does it mean to say I'm in the state L equals 0, M equals 0? What is that telling you? 0 angular momentum, right? What's the expectation value of L squared? 0. The expectation value of LZ. And by rotational invariance, the expected value of LX or LY. That thing is not rotating. There's no angular momentum, right? So the no angular momentum state is one with L equals 0, M equals 0. So this is not spinning. What about this guy? L equals 1, M equals 0. Does this thing carry angular momentum? Yeah, absolutely. So it just doesn't carry angular momentum in the z direction. But its total angular momentum, on average, its expected angular momentum, total angular momentum, is LL plus 1, which is 2 times h bar squared. Yeah. So if you measure LX and LY, what do you expect to get? Well, if you measure LX squared or LY squared, you probably expect to get something non-zero. We'll come back to that in just a second. And what about the state L equals 1, M equals 1? Your angular momentum, you've got as much angular momentum in the z direction as you possibly can. Right? So that definitely carries angular momentum. So there's a state that has no angular momentum in the z direction. There's a state that has some, and there's a state that has less. Right? That makes sense. Yeah.
The M equals 1, L equals 1, yes, means that the angular momentum in the z direction is the total angular momentum.
Is it?
And LX and LY.
That's okay. That's an excellent question. So let me come back to that. Well, let me answer that now, and I'll come back to the point I wanted to make. Okay, hold on a second. We just answer that question. Oh, good. So I'll work here. So here's the crucial thing. Even in the state, so here we were talking about, you were asking about the state L equals 1 and N equals 1. And the question that was asked, the very good question is, look, does that mean all the angular momentum is in the z direction? And L and LY are 0. Okay, but let me just ask this more broadly. Suppose we have a state with angular momentum L and M is equal to L. Okay, the most angular momentum we can possibly have in the z direction. Same question. Is all the angular momentum in the z direction? And what I want to emphasize to you is no, that's absolutely not the case. So, two arguments for that. The first is, suppose it's true that LX and LY are identically 0. Okay, can that satisfy the uncertainty limit?
Hold on a second.
Do those commutators? No, there must be uncertainty in LX and LY because LZ has a non-zero expectation value. So it can't be that LX squared and LY squared have 0 expectation value. But let's be more precise about this. The expectation value of L squared is easy to calculate. It's h bar squared, LL plus 1. Right? Because we're in the state YLM. This is the state Y, L sub L, or LL. The expectation value of LZ squared is equal to h bar squared M squared, and M squared now M is equal to L, so h bar squared L squared. Aha! So the expected value of L squared is not the same as LX squared, but this is equal to the expected value of LX squared plus LY squared plus LZ squared. Which is equal, so therefore, the expected value of LX squared plus the expected value of LY squared is equal to, well, the difference between this and this, we just subtract this off, h bar squared L plus 1 is h bar squared L squared, h bar squared L. And by symmetry, you don't expect the symmetry to be broken between Alex and Ly. You can actually do the calculation and not just be glib about it, but both arguments give you the correct answer. The expectation value of Lx squared is equal to 1/2 h bar squared L. And 0 for y in this state. So notice two things. First off, is we made the total angular momentum little l large. The amount by which we fail to have all the angular momentum in the z direction is getting larger and larger. We're increasing the crappiness of putting all the angular momentum in the z direction. However, as a ratio of the total angular momentum divided by L squared, so this divided by L squared, and this is h bar squared L plus 1, and here this is L squared plus L. So if we took the ratio, the rational mismatch is getting smaller and smaller. And that's good, because as we go to very large angular momentums, where things should start getting classical in some sense, we should get back the familiar intuition that you put all the angular momentum in the z direction. Okay. Yeah?
Why are we imposing this intuition at the expectation value of no one data?
Excellent. That's why I'm saying this is a glib argument. You don't have to vote that. That needs to be done a little more delicately, but we can just directly compute this and you do it on your problem set.
Why doesn't the existence of the L equals 0 environment where the angular momentum where L squared is definitely 0 violate the uncertainty?
Awesome. On your problem set, you're going to answer that. Let me give you a quick preview. This is such a great response. So let me give you a quick preview. So from that Alex, okay, this is a really fun question. Let me go into it in some detail. We're going. Wow, I'm going fast today. Am I going way too fast? You know, a little too fast. Okay, ask me more questions to slow me down. I'm excited. I didn't get much sleep last night. So yesterday, one of the great joys of being a physicist is working with other physicists. So yesterday, one of my very good friends in Cloudberry, I really delight in talking with, came to visit. We had a late night dinner, and this led to me late at night, not doing my work, but reading papers about what our conversation was about. And only then, at the very end, when I was just about to die, did I write the response to the reviewer on the paper that I was supposed to be doing by last night. So I'm kind of tired, but I'm in a really good mood. It's a really good job. Okay, so now I'm totally lost. What was the question again? Excellent. And the uncertainty. Good. So the question is, why don't we violate the uncertainty when we know that L equals, where am I? Just covered it. When we know that L equals 0 and N equals 0, doesn't that destroy our uncertainty? So we know that the angular momentum for LZ is 0, angular momentum for LX is 0, angular momentum for LY is 0. All of them vanish. Doesn't that violate the uncertainty principle? So let's remind ourselves what the form of that uncertainty relation is. The form of the uncertainty relation following from LX, LY is IH bar LZ. Recall the general statement. The uncertainty in X, or the uncertainty in A, times the uncertainty in B, squared, is equal to, what we squared is H bar upon 2, sorry, 1/2. The absolute value of the expectation value of the commutator, A with B, right? Good lord. Okay. Dimensionally, does this work? Yes. Okay, good, because units of A, units of B, units of A, units of B. Triumph. And these are going to be quantum mechanically small because commutators have H bars. When commutators have H bars, why? Not because God hates us. Why do commutators have H bars? What happens classically? In classical mechanics, do things commute? Yes. Why are there commutators H bars and commutators of physical observables? Because we exist. Right? Because there's a classical limit. Okay, so this is going to be quantum mechanically small, so we expect the uncertainty relation to also be quantum mechanically small. Okay, just important intuition. So let's look at the specific example of Lx, Ly, and Lz. So the uncertainty in Lx, in any particular, remember that this is defined as the uncertainty in a particular state psi, and this expectation value is taken in a particular state psi, that same state. So the uncertainty of Lx in some state ylm times the uncertainty of Ly in that same state ylm should be equal to, sorry, greater than or equal to 1/2 the absolute value of the expectation value of the commutator of Lx and Ly. The commutator of Lx and Ly is I H bar LT, and I, when we pull it through this absolute value is going to give me just 1, H bar is going to give me H bar upon 2, expectation value of LZ, absolute value. Yeah? So, can Lx and Ly have 0 uncertainty?
Yes.
Can Lx and Ly have 0 uncertainty?
Yes.
When? LZ, expectation value of LZ is 0. So that sounds good. It sounds like we could have LZ, if LZ has expectation value 0, then we can have Lx and Ly definite. But that's bad. Really? Really? Can we do that? Why not? Bless you, my son. So can we have Lx and Ly both get definite values just because LZ? Why? What else do we have to satisfy? What other uncertainty relations must we satisfy? There are 2 more, okay? And I invite you to go look at what those 2 more are and deduce that this is only possible if Lx squared, Ly squared, and Lz squared all have 0 expectation value. In fact, I think it's such a great question that I think it's on your problem set. Okay? So thank you for that question. It's a really good question. There was another question in here. Yeah.
So something you said earlier,
Yes. Okay, great. So the question is, wait, really? Why is L an integer or half integer? That was a little too quick. Is that roughly the right statement? Yeah, good, excellent. So let me go through the logic. So logic goes like this. I know that the YLMs, if the YLMs are eigenfunctions of L squared and LZ, and I've constructed this tower of them using the raising and lowering operators, we've already shown that the largest possible value of M is L, and the least possible value is minus L. And these states must be separated by integer steps in N. Right? Okay, good. So let the number, pick a value of L, okay, a particular tower, and let the number of states in that tower be n sub L. Okay, so there's n sub L, then great. And what's the distance between these guys? Well, we haven't seen L's integer yet. We haven't seen that yet. Okay. So this n sub L is an integer because it's the number of states. The number of states can be, pi. So now let's count this. So how many states are there? NL. But if I count 1, 2, 3, 4, the total angular momentum down here is 2L. Okay. So I had some pithy way of giving this a fancy name, but I can't remember what it was. Okay. So the length of the tower in units of h bar, the height of this tower is 2L. But the number of steps I took in here was NL minus 1. And that number of steps is times 1. So we get a 2L is n minus 1. There's nothing fancy here. I'm just saying if L is 0, we go from here to here, right? There's just one element. So number of states is 1, L is 0. So it's that same logic just repeated for every value of L. Other questions? Okay. So coming back to this, something on this board should cause you some serious physical discomfort. So we talked about the L equals 0, M equals 0 state. This is a state which has no
M equals 1 half.
at all. Talked about the L equals 1, N equals 0 state. It carries no momentum in the z direction, but it presumably has no direct rotation value for L squared, x and L and y squared. These guys are also fine. What about these guys? Yes. That's disconcerting. Do I have to have angular momentum in the z direction? That should go on a shirt somewhere. Let me ask a question more precisely, or in a way that's a little less threatening to me. Do you have to have angular momentum in the z direction? Okay. I'm sorry, what's your name? Does Nathan need to have angular momentum in the z direction? Does this chalk need to have angular momentum? Well, the chalk's... Okay, classically, no, right? Okay, it can have some total angular momentum which is 0, and it can be rotating not in the z direction. It can be rotating in the z, y, or the zx plane. If it's rotating in the zx plane, it's got angular momentum. Total angular momentum L squared is not 0, but its angular momentum in the z direction is 0. Its axis is exactly along the y direction, right? And so it's got no angular momentum. That's perfectly possible classically, and that's perfectly possible when L is an integer. Similarly, when L is 2. This is the particular tower that I love the most. 2, 1, 0, minus 1, minus 2. The reason I love this the most is that it's related to gravity, which is pretty awesome. Yeah, that's a whole other story. I really shouldn't have said that. So that's only going to confuse you. So for any integer, it's possible to have no angular momentum in the z direction. That means it's possible to rotate around the x-axis or the y-axis. We're talking about the z-axis. That makes sense. But for these half integer guys, you are inescapably spinning. There is no such thing as a state of this guy that carries no angular momentum. Anything well described by these quantum states is perpetually rotating or spinning. It carries angular momentum. Essentially, perpetually carries angular momentum in the z direction. Anytime you measure, it carries angular momentum either plus a half integer or minus a half integer. Never, ever 0.
But in the classical limit where you have a very large L, the n equals 1 half state, or the n equals minus half state is going to get arbitrarily small compared to the angular momentum. So is it just like where we said, well, okay, you can never have your angular momentum only in the z direction, but we don't care because in the classical limit it gets arbitrarily close to.
See, one of the nice things about writing lectures like this is that you get to leave little landmines. So this is exactly one of those. Thank you for asking this question. So let me rephrase that question. Look, we all took high school chemistry. We all know about spin. The nuclei have spin. They have some angular momentum. But if you build up a lot of them, you build up a piece of chalk. Look, as we said before, while it's true that the media carries there's some mismatch in the angular momentum in the z direction for some large L state. It's not only angular momentum. Some is in LZ, LX, and LY as well. It's preposterously small for a macroscopic object where L is macroscopic. It's meant the angular momentum Planck units in units of the Planck constant, 10 to the 26. I mean, something huge. Why would we even notice? But here's the real statement. The statement isn't just that this is true of macroscopic objects, but imagine you take a small particle. Imagine you take, a single atom. We're deep in the quantum mechanical regime. We're not in the classical regime. You take that single atom, and if it's described, if it carries angular momentum, it's described by the L equals 1 half state, that atom will never, ever, ever be measured to have its angular momentum in the z direction, or indeed in any direction, be 0. You will never, in any direction, measure its angular momentum to be 0. That atom perpetually carries angular momentum, and that is weird. Okay, well, maybe you don't find it weird. This is good. You've grown up in a year, and that's not a weird thing. But I find this deeply disconcerting. And one reason you might say, well, look, we never actually measure them, but we do. We do all the time because we measure things like the spectra of light, as we'll study when we study atoms in a couple of weeks because of the exam. Sorry, guys, there has to be an exam. As we will find when we study atoms in more detail, we did it all. We'll be sensitive to the angular momentum of the constituents of the atom, and we'll see different spectra. So it's an observable property when you shine light on, gases. This is something we can really observe. So what this suggests is one of two things. Either these are just crazy, right, and ridiculous, and we should ignore them, or there's something interesting and intrinsically quantum mechanical about them that's not so familiar. And the answer is going to turn out to be the second, the latter of those. The latter? That was not intentional. Maybe it was subconscious. Okay, so I want to think about some more consequences of the structure of the YLMs and the eigenvalues, in particular of this power structure. I want to understand some more what other physics can we extract from this story. So first, a very useful thing is just to get a picture of these guys in your head. Let's draw the angular momentum eigenfunctions. So what does that mean? Well, first, when we talked about the eigenfunctions of momentum, linear momentum in one dimension, we immediately went to the wave function. We talked about how the amplitude to get a particular spot varied in space, right? And the amplitude was just e to the ikx. So the amplitude was an oscillating phase rotated, and the absolute value of the probability had to be completely constant. Remember that? That was the 1D plane. So the variables that we had an angular momentum eigenstate, and that's a function of the position. Or sorry, a linear momentum eigenstate, that's a function of position. Angular momentum eigenstates are going to be functions of angular position. So I want to know what these wave functions look like, not just the eigenvalues, but I want to know what is the wave function associated to eigenvalues little l look like, y sub lm of the angular state at phi. What do these guys look like? So how do we get them? So this is going to be our goal for the next few minutes. So the first thing to notice is that we know that we know what the form of the eigenvalues and eigenfunctions are. If we act with LZ, we get h bar m back. If we act with L squared, we get h bar squared L plus 1 back. But we also have other expressions for LZ and L squared. In particular, I wrote them down last time in spherical coordinates. So I'm going to work in spherical coordinates where the declination from the vertical is an angle theta, and the angle around the equator is an angle phi. Okay. And theta equals 0 is going to be up in the z direction. It's just a choice of coordinates. There's nothing deep. There's nothing even shallow. It's just definitions. So we're going to work in spherical coordinates, and in spherical coordinates, we observed that this angular momentum, just following the definition from r cross p, takes a particularly simple form. That's a typo. H bar upon I, dd phi. Okay. And instead of writing L squared, I'm going to write L plus minus because it's shorter, and also because it's going to turn out to be more useful. So this takes the form H bar e to the plus minus I phi d theta plus or minus cotangent of theta d phi. Okay. So these are the
phi. Do I have the opposite route there? Fine, sine, maybe I have the opposite. Right now, let me just go back. I wasn't paying attention when he was drawing it. I was just assuming.
And L squared. In particular, I wrote them down last time in spherical coordinates. So I'm going to work in spherical coordinates where the declination from the vertical is an angle theta, and the angle around the equator is an angle phi.
Okay, yeah.
And theta equals 0 is going to be up in the z direction. It's just a choice of coordinates. There's nothing deep. There's nothing even shallow. It's just definitions. Just following the definition from r cross p. It's a particularly simple form. That's a typo. H bar upon I, dd phi. Okay. And instead of writing L squared, I'm going to write L plus minus because it's shorter, and also because it's going to turn out to be more useful. So this takes the form H bar e to the plus minus I phi d theta plus or minus cotangent of theta d phi. Okay. So these are the expressions for LZ and L plus minus in spherical coordinates, in these spherical coordinates. So I want to know how YLM depends on theta and phi, and it's clearly going to be easier to ask about the LZ eigenequation. So let's look at that. LZ on YLM, sorry, LZ on YLM gives me H. Oh yeah. Oh Jesus. When I write letters by hand, which it's like basically when I write to my mom, all my H's are crossed. I can't help it. So this is like the inverse. It's been a long time since I made that mistake. It's usually the other. Okay, so LZ acting on YLM gives me H bar M acting on YLM. But that's when I go and act with LZ, so let's just write out the differential equation. So H bar M YLM, where M is an integer or a half integer, depending on whether L is an integer or a half integer. H bar M YLM is equal to H bar upon I d phi of YLM. Okay. Using the awesome power of division and multiplication, I will divide both sides by H bar. and I'll multiply both sides by I. Okay. And we now have the equation for the eigenfunctions of LZ, which we actually wrote last time. And we can solve this very simply. This says that, remember, YLM is a function of theta and phi. Here we're only looking at the phi dependence because that's all that showed up in this equation. So this tells us that the eigenfunctions YLM are of the form of theta and phi, are of the form e to the im phi times some remaining dependence on theta, which I'll write as p of theta. And that p could depend on L and M. Cool? Before we even ask about the dependence on theta, the p dependence, we learned something pretty awesome. Look at this wave function. Okay? Whatever else we know, its dependence on phi is e to the im phi. Now, remember what phi is. Phi is the angle around the equator. So it goes from 0 to 2 pi. And when it comes back to 2 pi, it's the same point. Phi equals 0 and phi equals pi are two names for the same point. Yes? But that should worry you. Because note that as a consequence of this, y, lm, of theta 0 is equal to, well, whatever it is. But, theta of 2 pi is equal to e to the I m 2 pi times p ln theta. But this is equal to, oh, now we're in trouble. If n is an integer, this is equal to e to the I integer 2 pi, 1. Yes, okay. You're supposed to cheer at that point. It's like the coolest identity in the world. So e to the I 2 pi, that's 1. So if n is an integer, then this is just p lm of theta, which is also what we have by putting in phi equals 0. So this is equal to y lm of theta, comma 0. But if n is a half integer, then e to the I half integer times 2 pi is minus 1. And so that gives us minus y lm of theta and 0 if m is half integer. So let me see that. Again, in the same word actually. Again, with emphasis. What this tells us is that y lm at 0 as a function of the coordinates theta and phi. Y lm, so let's take m as an integer. Y lm at theta and 0 is equal to y lm at theta and 0. Right? That's good. But if m is a half integer, then y lm at theta and 2 pi, which is the same point as y lm at theta and 0, is equal to minus y lm at theta and pi, at theta and 0. That's less good. What must be true of y lm? Theta 0. 0. And was there anything special about the point 0? That could just be any point and rotated around the pi. So this tells us that y lm of theta and phi is identically equal to 0 if m is a half integer.
That sounds bad.
Huh. That's bad. Right? Because what's the probability density being found at any particular angular position? 0. Can you normalize that state? No. That is not a state that describes a particle. That is a state that describes the absence of a particle. That is not what we want. So these states cannot describe these values of L and M, which seem like perfectly reasonable values of L and M, perfectly reasonable eigenvalues of L squared and L M. They cannot be used to label wave functions of physical states corresponding to wave functions on a sphere. We can't do it. Because if you try, you find that those wave functions identically vanish. Okay? So these cannot be used. These do not describe wave functions. These do not describe wave functions of a particle in quantum mechanics. They cannot be used. Those values, those powers, cannot be used to describe particles moving in 3 dimensions. Everyone, so questions about that? That is a slightly subtle argument. Yeah.
You used to say earlier about how atoms that never have a zero angular momentum, and so the ones that have the zero angular momentum is going to also start.
Excellent question. That's a slightly silly question. Look, earlier you were saying, yeah, atoms can have, there are atoms in the world and they have half integer angular momentum, and you can shine light on them, you can tell, and stuff. But you just said you can't, these can't exist, so how can those two things both be true? And I actually think this question is a very good question. I actually said a slightly different thing. What he said was, states with angular momentum Lm are half integers cannot be described by a wave function of the coordinates. We're going to need some different description. And in particular, we're going to need a different description that does what? Well, as we take phi from 0 to 2 pi, as we rotate the system, right? As we take phi from 0 to 2 pi, rotate the system, we're going to think about minus sign. So in order to describe an object with Ln being a half integer, we can't use a wave function. We need something that is allowed to be doubly valued. And if you need something that behaves nicely when you rotate around by 2 pi, we need to come back to a minus sign, not itself. So it's some object that's not a function. It's called a spinner. So we'll talk about it later. We need some object that does that. So there's this classic demonstration at this point, which is supposed to be done in the quantum mechanics class. So at this point, the lecturer is obliged to do the following thing. You say, blah, blah, blah. If things rotate by 2 pi, they have to come back to themselves. And then you do this. Okay. I'm going to rotate my hand like a I don't know, record by 2 pi, and it will not come back to itself. Okay. And quite uncomfortably to not come back to itself. Okay, but I can do a further rotation to show you that the minus sign can do a further rotation by 2 pi and have it come back to itself. Right? And attempt to act as vertical, yeah? Okay, so I think we're all supposed to like, oh yes, yeah. Okay, so now that we've got that out of the way, I have an arm. Okay, so the story's a little more complicated than that. This is actually a fair demonstration, but it's a slightly subtle story. If you want to understand it, ask your rotation instructor. Yeah. You want B6?
They don't go with these
What about USB sticks? You serve this way, they don't work. You serve them this way, they don't work. If you do it again, then they do. Okay. That's pretty good. Okay. So for the moment, as long as we want to describe our system with a wave function position, which means we're thinking about where will we find it as a function of angle, we cannot use a half integer Ln. So if we can't use a half integer Ln, fine. We'll just throw it out for the moment, and we'll use the integer Ln, and let's keep going. Okay, now what we need to determine now is the p. We determine the phi dependence, we'll get the theta dependence. We can get the theta dependence. And it's in a sneaky fashion. Remember, when you solve remember that the harmonic oscillator in 1D, when we wanted to find the ground state wave function, we got to solve the energy eigenvalue equation, which is a second order differential equation, and kind of horrible, right? Or we could solve the ground state equation that said that the ground state is annihilated by the annihilation operator, which is a first order differential equation, much easier to solve. Yeah? Let's do the same thing. We have an annihilation condition. If we have the top state, L plus on YLL is equal to 0. But L plus is a first order differential operator. This is going to be easier. So we need to find a solution to this equation. And so I want to go through this. Yeah, now. Okay, so I want this equal to 0, but L plus YL is equal to, well, it's h bar e to the plus I phi d theta plus cotangent theta d phi on YLL. YLL is e to the I L phi times p Lm plus theta. Cool. So GD phi on e to the I L phi, there's no phi dependence here. It's just going to give us a vector of IL. So to make Yeah. So that's going to give us a plus IL, no dd phi. IL. And then this. The IL phi we can pull out. But this has to be equal to 0, so this says that 0 is equal to d theta plus IL. Cotangent theta p ln. Of theta. And this is actually much better than it seems for the following reason. dd theta, fine, that's dd theta. Cotangent of theta is cosine over sine. That's what you get if you take the derivative of lots of sine functions, sine to the L, say, take the derivative, you lose the power of sine, you pick up the power of cosine. So multiplying by cotangent gets rid of the power of sine, gives you a power of cosine, which is the derivative of sine. So PLM, noticing the L.
How did we drop? I guess we just divided out by.
And I screwed up an I somewhere. I think I wanted an I up here. Let's see. I. Sorry. Yes, I want an I cotangent.
Let me just adjust my notes here.
Okay, that's much better. So I cotangent, and then good. And then the I squared is giving me a minus L. Good. And this tells us that PLM. So if this is sine to the L, then d theta gives us an L sine to the L minus 1 cosine, which is what I get by taking sine to the L and multiplying by cosine, dividing by sine, multiplying by L. So this gives me PLL. This is for the particular state, LL.
When does this happen? This is at 104. 104. All right, PLL. I guess this is LL.
We'll look at the top state when annihilating it, so PLL is equal to some coefficient, closed state proportional to sine to the L of theta. So this tells us that YLL is equal to some normalization, some LL, just a number, times from the phi dependence into the IL phi, and from the theta dependence sine to the L of theta. Okay. So this is the form. This is the form. Oh, sorry, go ahead. This twisted horrible thing is proportional to. But, it was a long night. So now we have the wave function explicitly. So for the top state in any tower, right? This is for any L. The top state in any tower is e to the IL phi. Does that make sense? Well, LZ is h bar phi d phi, so that gives us h bar is m is L. That's good. That's the top state. And from the sine theta, we just checked. We constructed that this indeed has if you then check, you will find that the L squared eigenvalue, which you'll do in the problem set, the L squared eigenvalue is h bar squared L plus 1. Yeah.
Good question. When the expression have the L plus minus operators, that we construct the expression for L and L1.
Good. So it's much easier than you think. So Lx is equal to it's R cross L cross B. So this is going to be YTC minus CP1. Yeah. But you know what? So and this is equal to h bar phi y d z minus z dy. when you know what y is in spherical coordinates, and you know what derivative with respect to z is in spherical coordinates, you know what z is, and you know the chain rule. So taking this and just plugging in the explicit expression for the chain of variables to spherical coordinates takes care of it. Yeah. Sorry, this is bad notation. It's not bad notation. It's just not familiar notation. So it's notation that is used throughout theoretical physics. It means this: sine theta to the L power of sine. Yeah. For typesetting reasons, we often put the power before the argument. Yeah, no, it's a very good question. Thank you for asking because it was unclear. I appreciate that. Other questions? Yeah. How do we come up with the L hat plus minus? That was from this. Yeah. So we know what the components of the angular are in Cartesian coordinates. And you know how to, because it's coordinates, you know how to change variables from Cartesian to spherical. So you just plug this in for Lx, but L plus is Lx plus I Ly. And so you just take these guys in spherical form and add them together with the relative I. And that gives you that expression.
Maybe can you just explain the distinctions between y sub LL and y sub LM?
Yeah, absolutely. So y sub LL, it means y sub LM, where m is equal to L. It's a generic Hamming function of the angular momentum with the angular momentum in the z direction being equal to the angular momentum in the total angular momentum. So at least for these numbers. Okay, cool. Good. So now, if we know this, how do we just as a side note? Suppose we know this. We know this. We know what the top state of the tower looks like. How do I get the next state down to the tower? How do I get L minus 1? Lower it. Exactly. So this is easy. L minus on YLL. And we have to be careful about normalization. So again, it's proportional too. Okay. But this is easy. You don't have to solve any different equations. You just have to take derivatives. So it's just like the raising operator for a harmonic oscillator. We can raise and lower along the tower to get the right wave function. Okay. So to give you some examples. Yeah, let's see that here. So let me just quickly give you a few examples of the first few spherical harmonics. So sorry, I should give these guys a name. These functions, YLM and theta and phi, they're called the spherical harmonics. They're called these because they solve the Laplacian equation on the sphere, which is just the eigenvalue equation. L squared on them is equal to a constant to put those things back. So, so just to tabulate a couple of examples for you concretely, consider the L equals 0 states. So y, what are the lab values of m for little L equals 0? 0. So y 0, 0 is the only state, and if you properly normalize it, it's 1 over root 4 pi. Okay, good. What about L equals 1? Then we have y0, all right, y10. And we have y1 minus 1, and we have y1, 1. So these guys take a purely simple form. Root 3, I'm not even going to worry about the coefficient. They're in the notes. You can look them up anywhere. Times cosine. So first off, actually, let's look at y11. So y11 is going to be some normalization. And what is the form? Right, so it's just e to the I L phi sine theta to the L. L is 1. So this is some constant times e to the I phi sine theta. y10. Well, it's got angular momentum 0 in the z direction, in LZ. So that means how does it depend on phi? It doesn't. And you can easily see that because we're going to lose when we lower, we get an e to the I minus I phi. Anyway, so this gives us a constant times no e to the I phi dependence and cosine of theta. And it's easy to see cosine theta, the d theta and the cotangent d phi both give you the same thing. And y1 minus 1 is again a constant times e to the minus I phi. So it's got m equals minus 1 and sine theta again. Notice a pleasing sort of parsimony here. The theta dependence is the same for plus f and minus f. Okay, and so what about y22? Some constant e to the I2 phi sine squared theta. That we got y0, 0. And here it's interesting. So here. We just got one term from taking the derivative, they both give you cosine. But now there are two ways to act with the two derivatives. And this gives you a constant. Now what's the phi dependence? It's nothing because it's got m equals 0. And so the only dependence is on theta. And we get a cos squared, oops, there's a 3. 3 cos squared theta minus 1. Oh, shoot, thank you. Yes, I mean y20. Thank you. And then if we continue lowering to y2 minus 2, this is equal to again a constant. And the only thing we have the same dependence on theta, but a different dependence on phi, the minus 2I phi sine squared theta. Okay? Yeah. Why? Good, so quick question. So let me turn that into a question. So the question is, are these normalizable? Yeah, okay, so how would we normalize them? What's the check if they're normalizable? Yeah, we integrate them norm squared over a sphere. Okay, not over a volume, just over a sphere. They're only wave functions on the sphere. We haven't dealt with the radial function. We'll deal with that later. That'll come in the next lecture. Other questions? Yeah. Yeah, so y m equals 0 doesn't have any phi dependence? Yeah, so if m equals 0 had phi dependence, then we know that the eigenvalue of LLZ is what we get when we take derivatives with phi. But if the LZ eigenvalue is 0, that means that when we act with dd phi, we get 0. That means it can't depend on phi. Cool? Okay. Other questions? What I'm going to do next is I'm going to show you, walk you through some of these angular momentum states graphically on the computer. Before we get any questions about the calculation so far. Okay, so here, so this mathematical package I'll post on the webpage, and at the moment I think it's doing the real part. So what we're looking at now is the real part actually looks at the absolute value. Okay, good. So here we are looking at the absolute value of. Oops, that's not what I wanted to do. Okay, so what we're looking at in this notation is some horrible parametric plot. You don't really need to see the mathematical. Oh shoot. Sorry. Okay, so you don't need to see the code particularly, so I'm not going to worry about it, but it'll be posted. So here we're looking at the absolute value, the norm squared of the spherical harmonic y, and the lower eigenvalue here, lower coordinate is the L, and the upper is M.
So I'm going to draw these over here.
So when L is 0, what we get is what we're looking at. So here's what this plot is indicating. The distance away from the origin in a particular angular direction is the absolute value of the wave function. So the further away from the origin, the colored point you see is, the larger the absolute value. Okay? So, and the color here is just to indicate sort of depth and position. It's not terribly meaningful. So here we see that we get a sphere. So the probability depth here, the norm squared of the wave function, the spherical harmonic, is constant. So that makes sense. It's spherically symmetric. It has no angular momentum. As we start increasing the angular momentum, let's take the angular momentum, L is 1, and the 0 state. Now something interesting happens. Now the angle, so the total angular momentum is 1, and we see that there's two spheres. Let me sort of rotate this. So there are two spheres, and there's a z-axis passing through them. And so the probability is much larger around this lobe on the top or the lobe on the bottom, and it's 0 on the plane. Okay. Now that's kind of non-intuitive if you think, well, LZ is large, so it should be, you know, why is it low invertible? So why is that true? So here, this is the LZ equals 0 state. That means it carries no angular momentum along the z-axis. That means it's not rotating far out in the xy plane. So your probability of finding it in the xy plane is very small. Because if it was rotating in the xy plane, it would carry large angular momentum LZ, but its LZ is 0. So it can't be extended out in the xy plane. Cool. On the other hand, it can carry angular momentum in the x or the y direction. But if it carries angular momentum in the x direction, for example, that means the system is rotating around the z. Sorry, if it carries angular momentum in the x direction, it's rotating in the z, y plane, right? So there's some probability to find it out of the plane in y and z, but it can't be in the x, y plane. Hence, it's got to be in the lobes up above. Is that cool? So it's very useful to develop an intuition for this stuff if you're going to do chemistry or crystallography or any kind of physics. It's just very useful. So I encourage you to play with these little applets, and I'll post this mathematics package. Let's look at what happens now if let's crank up the angular momentum. So as we crank up the L angular momentum, now we're getting this sort of loamy thing, which looks like some sort of 50s sci-fi.
This is 2, 0 to 1.
You know, apparatus. So what's going on there? So now we see, so this is the 2, 0 state. And the 2, 0 state has a 3 code squared theta minus 1. For code squared theta, that means it's got 2 periods as it goes from vertical to negative. And if you take that and you square it, you get exactly this. Okay? So there you're seeing the code squared as a function of the angle of declination for vertical. And it's 0, it's n equals 0, so you're seeing no dependence on phi. And of course, that's a little cheap because the angular dependence on phi is just an overall phase. So we're not going to see it in the absolute value. Everyone agree with that? We're not going to see the absolute. Okay. So let's check that. Let's take L2 and M2. So now when L is 2 and M is 2, we just get this donut. So what that's saying is, look, all the angular, we've got some angular momentum L's too, but all the angular momentum, almost all of it anyway, is in the z direction. And if that were, we're seeing here, well, yeah, it seems like it's most likely to find the particle. The probability is greatest out in this donut around the point. Now, if it were LZ is equal to L, it would be flat. It would be a strictly zero thickness pancake. And we have some uncertainty in what L, X, and Ly are, which is why we get this fat donut. Ever cool that? And if we crank up L, and we make, yeah, right? So you can see that you get some complicated shapes. Okay, but as we crank up L and crank up M, we just get a thinner and thinner donut. And the fact that the donut's getting thinner and thinner is that L over L squared that we did earlier. Cool? It's still a donut, but it's getting relatively thinner and thinner, even though by virtue of getting wider and wider. And a last thing to show you is, let's take a look now at, in fact, let's go to the alpha zero state. Let's take a look at the real part. So now we're looking at the real part, and nothing much changed for the y00. But for y20, well, still not much change. For y20, let's now, so this is sort of disheartening. Nothing really has changed. Why? Because it's real, exactly. So for y20, as long as m is equal to 0, this is real. There's no phase. The phase information contains information about the LZ eigenvalue. So we can correct this by we can correct this by changing the angular momentum. Oh shoot, how do I do that? I can't turn it off. Okay, whatever. So here we have large M. Here we have large M, and now we've got this very funny Logie structure. So this is the y22, which a minute ago looked rotationally symmetric, and now it's not rotationally symmetric. It's this Logie structure, and where the lobes are. Remember, previously we had a donut. Now we have these lobes when we look at the real part. How does that make sense? Well, we've got a sine squared of theta. We've got an EZI to 2 phi, and if we look at the real part, that's cosine of 2 pi. And so we're getting a cosine function modulating the donut. If we look at the real part, let's do the same thing. Let's look at y22 and look at the imaginary part. And the imaginary part of y20, we get nothing. That's good because y20 was real. Right? That would have been bad. But if we look at the imaginary part of y22, we get the corresponding lobes, the other lobes, so that cos squared plus sine squared is 1. Okay? Play with these, develop some intuition. They're going to be very useful for us when we talk about hydrogen and the structure of solids. And I will see you next week.
All right, so definitely some stuff that I didn't understand entirely from here. So some of that is going to be this derivation. I'm just going to put a little mark here. But let's just try to think through this one here. This one is saying that because we are because we don't have because this z is not, then we have some kind of, so it means we might be rotating this way or this way, but not this way. So we'll put like this. So some, and I'll just put like this. And this one is going to be the same thing, but it's even more. I'm not sure why these change shapes. This one here is the opposite. I have to think about that a little bit more. I'm just going to put okay. I think I can just move on now to lecture 17. Not to say that there is not some parts here that don't need some clarification, because I think a lot of this stuff with figuring out what the eigenstates look like for the angular operator, or for the angular momentum, a lot of this stuff here, it's not entirely obvious to me, but I think I want to keep moving, and we can just go back later if I need to. So let me just open it up now.
The following
17.
content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right, should we get started? So, today, well, before we get started, so, I'll have questions from the last lecture where we finished off angular momentum. Or really anything up to the last exam. Yeah.
So what exactly happened to the half-L state?
What happened to the half-L state? Okay, great question. So we're going to talk about that in some detail in a couple of weeks. Let me give you a quick preview. So, remember that when we studied the commutation relations, L plus or L x, Ly is I H bar, LT, without using the representation in terms of derivatives with respect to reporting, without using the representations in terms of translations and rotations along the sphere. Right? When we just used the commutation relations and nothing else, what we found was that the states corresponding to these guys came in a tower. We had one state corresponding to little L equals 0, or two states with L equals 1/2, or three states with little L equals 1, or four states with L equals 3/2, and so on and so forth. And we quickly deduce that it is impossible to represent the half-integer states with a wave function which represents probability distribution on the sphere. We observed that that was impossible. And the reason is, if you did so, then when you take that wave function, if you rotate by 2 pi in any direction, if you rotate by 2 pi, the wave function comes back to minus itself. But the wave function has to be equal to itself at the same point. The value of the wave function at some point is equal to the value of the wave function at some point. That means the value of the wave function must be equal to minus itself. That means it must be 0. So you can't write a wave function which is probability distribution on a sphere if the wave function has to be equal to minus itself at any given point. So this is a strange thing. We sort of said, well, look, these are some other beasts. But the question is, look, these furnish perfectly reasonable towers of states respecting these commutation relations. So are they just wrong? Are they just meaningless? What we're going to discover is the following. This is really going to go back to the very first lecture. And so we'll do this in more detail. But I'm going to quickly tell you. Imagine you take a magnet, okay, a little tiny bar magnet. In fact, well, imagine you take a little bar magnet with some little magnetization, and you send it through a region that has a gradient for magnetic field. If there's a gradient, so you know that a magnet wants to anti-align with the nearby magnet. North-south wants to go to south-north. So you can't put a force on a magnet, but if you have a gradient of magnetic field, then one end of a dipole, one end of your magnet, can feel a stronger effective torque than the other guy, and you can get a net force. So you get a net force. The important thing here is that if you have a magnetic field which has a gradient, so that you've got some large B here and some smaller B here, then you can get a force, and that force is going to be proportional to how big your magnet is, but it's also going to be proportional to the magnetic field. And if the force is proportional to the strength of your magnet, then how far, if you send this magnet through a region, it'll get deflected in one direction or the other, and how far it gets deflected is determined by how big of a magnet you sent through. You send in a bigger magnet, it deflects more. Remember all that? Okay. Here's a funny thing. So that's fact 1. Fact 2. Suppose I have a system which is a charged particle moving in a circular orbit. Okay? A charged particle moving in a circular orbit. Or better yet, imagine you have a sphere. This is a better model. Imagine you have a sphere of uniform charge distribution. Okay? Little gelatinous sphere of uniform charge distribution. And you need to rotate. Okay? So that's charge that's moving, forming a current. And that current generates a magnetic field along the axis of rotation. Right-hand rule. So if you have a charged sphere and it's rotating, you get a magnetic moment. And how big is the magnetic moment? It's proportional to the rotation, the angular momentum. Okay? So you determine that for a charged sphere, a charged sphere which is rotating, with angular momentum, let's say L, has a magnetic moment which is proportional to L. Okay? So let's put this together. Imagine we take a charged sphere, we send it rotating with sending angular momentum, we send it through a field gradient for magnetic field. What we'll see is we can measure that angular momentum by measuring the deflection. Because the bigger the angular momentum, the bigger the magnetic moment, the bigger the magnetic moment, the bigger the deflection. Cool? So now here's a cool experiment. Take an electron. An electron has some charge. Is it a little pointing? Is it a little sphere? Is it, let's not ask that question just yet. It's an electron. The thing you get by ripping a negative charge off a hydrogen atom. So take the electron and send it through a magnetic field gradient. Why would you do this? Because you want to measure the angular momentum of this electron. You want to see whether the electron is a little rotating thing or not. So you send it through this magnetic field gradient, and if it gets deflected, you will have measured the magnetic moment. And if you measure the magnetic moment, you'll have measured the angular momentum. Okay? Here's the funny thing. If the electron weren't rotating, it would just go straight through, right? It would have no angular momentum, it would have no magnetic moment, and thus it would not deflect. Yeah? If it's rotating, it's going to deflect. Here's the experiment we do, and here's the experimental results. The experimental results are every electron that gets sent through bends, and it either bends up a fixed amount, or it bends down a fixed amount. It never bends more, it never bends less, and it certainly never bends 0. In fact, it always makes 2 spots on the screen. Okay? Always makes 2 spots, it never hits the middle. No matter how you build this experiment, no matter how you rotate it, no matter what you do, it always hits one of two spots. What that tells you is the angular momentum, rather than magnetic moment, can only take one of two values. But the angular momentum is just some geometric constant times the angular momentum. So the angular momentum must take one of two possible values. Ever go with that? So from this experiment, glorified as the Stern-Gerlach experiment, from this experiment we discovered that the angular momentum, LZ, takes one of two values, L along whatever direction we're measuring. Well, let's say in the z direction, L, LD, takes one of two values. Plus some constant, and plus h bar 0.2, or minus h bar 0.2. You just do this measure. But what this tells us is which state, which tower, which set of states describe an electron in this apparatus. That was 1/2. But wait, we started off by talking about the rotation of the charged sphere and deducing that the magnetic moment must be proportional to the angular momentum. And what we've just discovered is that this angular momentum, the only sensible angular momentum here, is the two-state tower, which can't be represented in terms of rotations on the sphere. Yeah. What we've learned from this experiment is that electrons carry a form of angular momentum, demonstrably, which is one of these angular momentum 1/2 states, which never doesn't rotate, right? It always carries some angular momentum. However, it can't be expressed in terms of rotation of some spherical electron. It has nothing to do with rotation, so it did. You get this nonsensical thing, the wave function identically vanishes. So there's some other form of angular momentum, a totally different form of angular momentum, at least for electrons, which again has the magnetic moment proportional to this angular momentum with some coefficient, which I'll call u0. But I don't want to call it L, because L we usually use for rotational angular momentum. This is a different form of angular momentum, which is purely half integer, and we call that spin. And the spin satisfies exactly the same commutation relations. It's a vector Sx with Sy is equal to I h bar Z. So it's like an angular momentum in every possible way, except it cannot be represented as Z does not have any representation in terms of h bar 1 d. It is not related to a rotation. It's an intrinsic form of angular momentum. An electron just has it. So this way you can ask me, look, what do you mean an electron just has it? And my answer to that question is, if you send an electron through a Stern-Gerlach apparatus, it always takes one of two spots. And that's it. It's an experimental fact, and this is how we describe that experimental fact. And the legacy of these rotation of these little 1/2 states is that they represent an internal form of angular momentum that only exists one mechanically. You would have never noticed in class. That was a very long answer to what was initially a simple question, but we'll come back and do this in more detail. So just a quick, yeah.
So for equals 3/2, is that because more don't exist?
Yeah, these are source values. And so there are plenty of particles in the real world that have L equals 3/2. They're not fundamental particles, as far as we know. There are particles in nuclear physics that carry spin 3/2. There are whole sorts of nuclei that carry spin 3/2. But we don't know a fundamental particle. If supersymmetry is true, then there must be a particle called the gravitino, which would be fundamental and would have spin 3/2 in 4 states. But that hasn't been observed yet. Other questions?
Is the ladder of two accessible states discovered first when the experiment? Can you explain that? The experiment?
Oh, no, that's a very good question. We'll have that in phase. If they were to do hydrogen among the things, although I've taken so long talking about this, we might be a little slow. We'll talk about it a little more when we talk about hydrogen, but it was observed and deduced from experiment before it was understood that there was such a physical quantity. However, the observation that this commutation relation led to towers of states with this pre-existed as a mathematical statement. So that was a mathematical observation from long previously. It has a beautiful algebraic story and all sorts of nice things, but it hadn't been connected to physics. And so the observation of the electron must carry some intrinsic form of angular momentum with one of two values, neither of which is 0, was actually an experimental observation, quasi-experimental observation, long before it was understood exactly how to connect this up. I shouldn't say long, it was like within months, but whatever. Sorry.
The experiment wasn't solved.
No, the experiment was this. There are the spectrum. Well, I'll tell you what the experiment was in a minute. Okay, yeah. Excellent. In this experiment, the thing that fixed the fact that I was probing LZ is that I made the magnetic field of a gradient in the z direction. So what I was sensitive to, since the force is actually proportional to mu dot v, or really mu dot the gradient to v. So we'll do this in more detail later. The direction of the gradient selects out which component of the angular momentum I'm looking at. So in this experiment, I'm measuring the angular momentum along this axis, which for fun I'll call z. I could call it x. When I discovered the angular momentum along this axis must take one of two values. But the universe is rotationally invariant. So it can't possibly matter whether I've done this experiment in this direction or done the experiment in this direction. What that tells you is, in any direction, if I measure the angular momentum of the electron along that direction, I will discover that it takes one of two values. This is also true of the L equals 1 states. LZ takes one of 3 values. What about LX? LX also takes one of 3 values. Those 3 values. Is every system in a state corresponding to one of those particular values? No, it could be in a superposition. But the eigenvalues are these 3 eigenvalues, regardless of whether it's LX or LY or LZ. It's a good thing to remember too. Anything else? One more, yeah. Indeed. Okay, since some people haven't taken the, so there will be a conflict exam later today, so I'm not going to discuss the exam. Yes. But very good observation and not an accident. Okay, so today we launch into 3D. We ditch our tricked out tricycle, and we're going to talk about real physical systems in 3 dimensions. And as we'll discover, it's basically the same as in 1 dimension. We just have to write down more symbols, but the content is all the same. So this will make obvious the reason we work with 1D up until now, which is that there's not a heck of a lot more to be gained for the basic principles, but it's a lot more known for time expressions. So the first thing we're going to do is write down the Laplacian in 3 dimensions in spherical coordinates. And that is a beautiful use of notation. In spherical coordinates. And I want to note a couple of things. So first off, this Laplacian, this can be written in the following form. 1 over r dr, r, quantity squared. Okay, that's going to be very useful for us, for this one. This is also known as 1 over r dr squared r. And this, if you look back at your notes, this is nothing other than L squared, except for the factor of h bar upon I. But if it's squared, it's minus 1 upon h bar squared. Okay, so this horrible angular derivative is nothing but L squared. And you should remember that dv theta is these funny sines and cosines. But just go back and compare your notes. So this is just an observation that the Laplacian in 3 dimensions in spherical coordinates takes the simple form. A simple radial derivative, which is 2 terms if you write it out linearly in this fashion, and 1 term if you write it this way, which is going to turn out to be useful for us. And the angular part can be written as 1 over r squared times the angular momentum squared with a minus 1 over h bar squared. Okay? So just to check, remember that LZ is equal to h bar upon I d phi. So LZ squared is going to be equal to minus h bar squared d phi squared. And you can see that that's one contribution to this piece. Actually, let me, I'm going to put a capital sin and erase what I just wrote. I didn't want to distract you. Okay. So, with that useful observation, I want to think about central potentials. I want to think about systems in 3D, which are spherically symmetric, because this is going to be a particularly simple class of systems, and it's also particularly physical. Simple things like harmonic oscillator in 3 dimensions, which we solved in Cartesian coordinates earlier, we're going to solve later in spherical coordinates. Things like the isotropic harmonic oscillator, things like hydrogen, where the systems are each independent, the force of the potential only depends on the radial distance, all share a bunch of common properties, and I want to explore those. And along the way, we'll solve a toy model for hydrogen. So the energy for this is p squared on 2m, plus a potential which is a function only of the radial distance. But now p squared is equal to minus h bar squared times the radiant squared. But this is going to be equal to from the first term, minus h bar squared. Let me just write this out. Minus h bar squared times r dr squared r. And then from this term, plus minus h bar squared times minus 1 over h bar squared L. Squared over r squared plus L squared over r squared. So the energy can be written in a nice form. This is minus h bar squared, norm upon r, dr squared, r. Upon 2m, p squared upon 2m. And for the second term, L squared over r squared upon 2m, plus 1 over 2m r squared, L squared, plus u of r. Okay, and this is the energy operator when the system is. Is rotationally invariant in spherical coordinates. Questions? Yeah. This? Oh, So that's an equal sign. So sorry, this is just quick algebra, so it's useful to know. So consider the following thing: 1 over r, dr, r. Why would you ever care about such a thing? Well, let's square it. Okay, because I did there. So what is this equal to? Well, this is 1 over r, dr, r. 1 over r, dr, r. These guys cancel, right? 1 over r times dr. This is equal to 1 over r, dr squared r. But why is this equal to dr squared plus 2 over r times dr? And the answer is they're operators, and so you should have to act on functions. So let's act how they act on functions. So dr squared plus 2 over r, dr times a function, acting on a function is equal to f prime prime, if this is a function of r, plus 2 over r, f prime. On the other hand, 1 over r, dr squared, r, acting on f of r. Well, these derivatives can hit either the r or the f. So there's going to be a term where both derivatives hit f, in which case the r's cancel and I get f prime prime. There's going to be two terms where one of the d's hits this, one of the d's hits this, then there's the other term. So there are two terms of that form. One d hits the r and gives me 1, one d hits the f and gives me f prime. And then there's an overall 1 over r plus 2 over r f prime. And then there's a term where 2 d's hit the r, but if 2 d's hit the r, that's 0. So that's it. So these guys are equal to each other. So why is this a particularly useful form? We'll see that in just a minute. So I'm cheating a little bit by just writing this out and saying this is going to be a useful form. Trust me, it's going to be a useful form. Yeah? Oh, shoot. Yes, that's supposed to be 1 over r. Thank you. Thank you. Yes. Over r. Thank you. Yes. Thanks for that technical correction. Excellent. Thanks. Okay. So anytime we have a system which is rotationally invariant, whose potential is rotationally invariant, we can write the energy operator in this fashion. And now you see something really lovely, which is that this only depends on r, this only depends on r. This depends on the angular coordinates, but only insofar as it depends on L squared. So if we want to find the eigenfunctions of E, our life is going to be a lot easier if we work in eigenfunctions of L. Because that's going to make this, when E acts on an eigenfunction of L, this is just going to become a constant. So now you have to ask the question, well, can we find functions which are eigenfunctions of E and of L simultaneously? And so the answer to that question is, well, compute the commutative. So do these guys commute, particular of L squared? And well, does L commute with the derivative with respect to R, L squared? Yeah, because L only depends on angular derivatives, it doesn't have any L any. And the R's don't care about the angular variables, so they commute. What about with this term? Well, L squared trivially commutes with itself, and again, R doesn't matter. And ditto, R and L squared commute. So this is 0, these commute. So we can find a common eigenbasis. We can find a basis of functions, which are eigenfunctions both of E and of L squared. So now we use separation. In particular, if we want to find a function, an eigenfunction of the energy operator, E phi E, is equal to E phi E. It's going to simplify our lives if we also let phi be an eigenfunction of the L squared. But we know what the eigenfunctions of L squared are. Phi E is equal to, when we write this of R, is going to be equal to little phi of R times YLM of theta and phi. Okay. Now, quickly, because this is these are the eigenfunctions of the L squared operator. Quick, is little L an integer or half integer?
Integer.
Why? Yeah, because we're working with rotational angular momentum, right? And it only makes sense to talk about integer values of little L when we have gradients on a sphere, when we're talking about rotations on the spherical coordinates. Okay? So little L has to be an integer. And from this point forward in the class, anytime I write L, I'll be talking about the rotational angular momentum corresponding to integer values. And when I'm talking about the half integer values, I'll write down x. Okay? So let's use this separation of variables. And what does that give us? Well, L squared acting on YLM gives us h bar squared LL plus 1 So this tells us that E, acting on phi E, takes us a particularly simple form. If phi E is proportional to a spherical harmonic, then this is going to take the form minus h bar squared upon 2m 1 over r dr squared r plus 1 over 2m r squared L squared, but L squared acting on the YLM gives us h bar squared L plus 1, which is just a constant over r squared plus u of r. Phi E. Question? Absolutely. So can we consider superpositions of these guys? Absolutely we can. However, we're using separation, so we're going to look at a single term, and then after constructing solutions with a single eigenfunction, we can then write down arbitrary superpositions of them and generate a complete basis of states. Gerald?
Just taking a quick bathroom break. I'll be right back. All right, I'm back. Let's continue.
Other questions? Okay. So here's the resulting energy eigenvalue equation. But notice that it's not really nice. This is purely a function of r. We've removed all of the angular dependence by making this proportional to YLM. So this has a little phi YLM, and this has a little phi YLM, and nothing depends on the little phi. So I can make this just, or nothing depends on the YLM, on the angular variables. I can make this phi r. Okay. And if I want to make this the energy eigenvalue equation, instead of just the action of the energy operator, that is now my energy eigenvalue equation. This is the result of acting on phi with the energy operator, and this is the energy eigenvalue. Okay. Cool? So the upshot here is that when we have a central potential, when the system is rotationally invariant, the potential energy is invariant under rotations, then the energy commutes with the angular momentum squared, and so we can find common eigenfunctions. When we use separation of variables, the resulting energy eigenvalue equation becomes nothing but a 1D energy eigenvalue equation. Right? This is just a 1D equation. Now you might look at this and say, well, it's not quite a 1D equation, because if this were a 1D equation, we wouldn't have this funny 1 over r and this funny r. Right? It's not exactly what we would have got. It's got the minus h bar squared upon 2m. Whoops, and there's it's got these funny h bar squared upon 2m, and it's got these 1 over r. Sorry, it's got the correct h bar squared upon 2m, but it's got this funny r and 1 over r. So let's get rid of that. Let's just quickly dispense with that funny set of r. And this comes back to the sneaky trick I was referring to earlier of writing this expression. So rather than writing this out, it's convenient to write it in this form. Let's see why. So if we have that E phi of r is equal to minus h bar squared on 2m, 1 over r d squared r plus. And now what I'm going to write is potential, U of R, this is some silly radial dependent thing. I'm going to write these two terms together rather than writing them over and over and over again. I'm going to write them together and call them V effective plus V effective. Of R, where V effective is just these guys. V effective. Okay. Which has a contribution from the original potential and from the angular momentum, which notice the sign is plus 1 over R squared, so the potential gets really large as you get to the origin. 5R. So this R is annoying, this 1 over R is annoying, but there's a nice way to get rid of it. Let 5R, well, this R we want to get rid of, so let 5R equal 1 over R, U of R. Okay. Then 1 over R squared, or sorry, 1 over R dr squared R, 5, is equal to 1 over R dr squared R times 1 over R times U, which is just U. But meanwhile, V on phi is equal to, well, V doesn't have any R derivatives, it's just a function. So V on phi is 1 over R, V on U. So this equation becomes E on U, because this also picks up a 1 over R, is equal to minus h bar squared upon 2m dr squared plus the effective of R U of R. And this is exactly the energy eigenvalue equation for a 1D problem with the following potential. The potential, V effective of R, does the following two things. Whoops, I want to draw that way. V effective of R. Suppose we have a potential which is the Coulomb potential. So let's say U is equal to minus E squared upon R. Just as an example. So here's R, here's the effective. So U first. So there's U. U of R. Let me draw this. V has another term, which is h bar squared LL plus 1 over 2 MR squared. This, for any given value of L, this is a constant over R squared with a plus sign. So that's something that looks like this. This is falling off like 1 over R, this is falling off like 1 over R squared. So it falls off more rapidly. And finally, can R be negative? No, it's defined from 0 to infinity. So that's like having an infinite potential for negative R. So our effective potential is the sum of these contributions. Wish I had colored chalk. The sum of these contributions is going to look like this. So that's my V effective. This is my 1 R squared or 2m R squared. This is my U of R. Question. Good. Okay, so this is U of R, the original potential. Okay. This is 1 over L squared, or sorry, LL plus 1 over 2 MR squared. shoot. Oh, I'm sorry. I'm terribly sorry. I've abused notation terribly. Listen. This is crap. Sorry. This is standard notation, and in text, when I write this by hand, the potential is a big U, and the wave function is a little u. So let this be a little u. Okay, this is my little u. And so now I'm going to have to, oh, geez, this is horrible. Sorry. This is the potential, capital U with a bar underneath it. Okay, seriously. So there's capital U with a bar underneath it. And here's V, which is going to make my life easier. This is the capital U with the bar underneath it. Capital U with bar underneath it. Oh, I'm really sorry. I did not realize how confusing that would be. Okay, is everyone happy with that? Yeah. Which one? Middle. Where? So these are the wave function. That's the wave function. That is V. And wait, if I erase it, how can I correct it? Excellent. So the thing that isn't here would have a bar under it. Oh, sorry. You wouldn't think it would be so hard. Okay, good. And this is not the wave function. Okay, God. Oh, that's horrible. Sorry, guys. That notation is not obvious. My apologies. There's a better way to do this. Okay, here's a better way to do this. Instead of calling it potential, I'm sorry, I'm like, your notes are getting destroyed now. So instead of calling potential capital U, let's just call this V. Yeah. And then we have V effective. No, this is good. This is good. We can be careful about this. So this is V. This is V effective, which has V plus the angular momentum. Oh, good Lord. This is V effective. This is V. V5 is VU. Good. This is V. There's no U underlying, it's not just V. V effective. Oh, good Lord. Okay. Wow, that was an unnecessary confusion. Top right. U. That's V. Although it would have been just as true for V effective, so we can write V effective. It's true for both. Because it's just a function of R. Oh, for the love of God. Okay. Let's check our sanity and walk through the logic. So the logic here is we have some potential. It's a function only of R. Yeah. As a consequence, since it doesn't care about the angles, we can write things in terms of the spherical harmonics. We can do separation of variables. Here's the energy eigenvalue equation. We discovered that because we're working in spherical harmonics, the angular momentum term becomes just a function of R with no other coefficients. So now we have a function of R plus the potential V. This looks like an effective potential, V effective, which is the sum of these two terms. So there's that equation. On the other hand, this is tantalizingly close to, but not quite the energy eigenvalue equation for a 1D problem with this potential V effective. To make it obvious that it's in fact a 1D problem, we do a change variables. Phi goes to 1 over RU, and then 1 upon R d squared R phi becomes 1 over R d squared U, and V effective phi becomes 1 over R V effective U. Plugging that together gives us this energy eigenvalue equation for U, the effective wave function, which is a 1D problem. So we can use all of our intuition and all of our machinery to solve this problem. And now we have to ask what exactly is the effective potential. And the effective potential has 3 contributions. First, it has the original V. Secondly, it has the angular momentum term, which is a constant over R squared. And here's that, constant over R squared. And the sum of these is V effective. And this guy dominates because it's 1 over r squared. This dominates at small r, and this dominates at large r if it's 1 over r. So we get an effective potential that I'll check. There's the effective potential. Okay. Boy. And finally, the third fact is that r must be strictly positive. So as a 1D problem, that means it can't be negative. It's got to have an infinite potential on the left. Okay. So as an example, let's go ahead and think more carefully about specifically this problem about this Coulomb potential and its 1D effective potential. Yeah. Yes. Remember that the DDR squared term gives 1 over r up front. So for this term, there should be 1 over r here. From this term, there should also be 1 over r. And from here, there should be 1 over r. So then I'm going to cancel 1 over r and multiply the whole equation by r. Yeah? Sneaky, sneaky. So anytime you see, this is a general lesson, anytime you see a differential equation that has this form, 2 derivatives plus 1 over r derivative, you know you can play some game like this. If you see this, declare in your mind a brief moment of triumph because you know what technique to use. You can do this sort of rescaling by power of r. And more generally, if you have a differential equation that looks like, let me do this here. If you have a differential equation that looks something like a derivative with respect to r plus a constant over r times phi, you know how to solve this. Let me say plus phi. You know how to solve this because ddr plus c over r means that phi, if there were nothing else equals 0, if there were no other terms here, then this would say ddr plus c over r is phi. That means when you do it, it's like divided by r multiplied by t. That means phi goes like r to the minus c. Right? But if phi goes like r to the minus c, that's not the exact solution to the equation. But I can write phi is equal to r to the minus c times u. And then this equation becomes ddr plus dot 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 u is 0. Okay? Very useful little trick. Not really a trick, it's just observation. And this is a secondary version of the same thing. Very useful things to have in your back pocket for moments of need. Okay? So let's pick up with this guy. So let me give you a little name for this. So this term that comes from the angular momentum bit, this originally came from the kinetic energy, right? It came from the L squared over r, which was from the gradient squared energy. This is a kinetic energy term. Why is there a kinetic energy term? Well, what this is telling you is that if you have some angular momentum, if little l is not equal to 0, then as you get closer and closer to the origin, the potential energy is getting very, very large. And this should make sense. If you're spinning and you pull your arms, you have to do work, right? You have to pull those guys in and you speed up. You're increasing your kinetic energy due to conservation of angular momentum. Right? If you have rotational invariance, as you bring in your hand, you're increasing the kinetic energy. And so this angular momentum barrier is just an expression of that. It's just saying that as you come to smaller and smaller radius, holding the angular momentum fixed, your velocity, your angular. Velocity must increase, your kinetic energy must increase, and we're calling that a potential term just because we can, because we've worked with definite angular momentum. Okay, you did this. You should have done this in classical mechanics as well, well, you should have done it in classical mechanics. So this is called the angular momentum barrier. Quick question: classically, if you take a charged particle around in a Coulomb potential, classically, that system decays, right? It radiates away energy. Does the angular momentum barrier save us from decaying? Is that why hydrogen is stable? No one wants to stake a claim here?
No.
Is hydrogen stable because of concentration of angular momentum?
No.
No, absolutely not. Right? So first off, in your first problem set, when the particle had angular momentum, So, and it can radiate that away through electromagnetic interactions. So that can save us. Angular momentum won't save us. Another way to say this is that we can construct it. We just explicitly see we can construct this state which has little L equals 0, in which case the angular momentum barrier is 0 over r squared. So it says nothing. Angular momentum barrier is not what keeps you from decaying. And the reason is that the electron can radiate away energy in angular momentum, and so L will decrease and decrease. It can still fall down. So we still need a reason for why the hydrogen system, quantum mechanically, is stable. Why do you think this is? So let's answer that question. So what I want to do now is I want to solve. Do I really do that way? Well, actually, before we do, let's consider some last general conditions. General facts for central potentials. So let's look at some general facts for central potentials. So the first is, regardless of what the bare potential was, just due to the angular momentum barrier, we have this 1 over r squared behavior near the origin. So we can look at this. We can ask, what are the boundary conditions at the origin? What must be true of u of r near the origin? Near u of r. Or sorry, near r goes to 0. What must be true of u of r? So the right way to ask this question is not to look at this u of r, which is not actually the wave function, but to look at the actual wave function, phi sub t, which goes near r equals 0, like u of r over r. So what should be true of u? Can u diverge? Is that physical? Does u have to vanish? Can it take a constant value? So I'm giving you a hint by telling you that I want to think about there being infinite potential, but why? Why is that the right thing to do? Well, imagine u of r went to a constant value near the origin. If u of r goes to a constant value near the origin, then the wave function diverges near the origin. Well, that's maybe not so bad. Maybe it has a 1 over r singularity. It's not totally obvious that that's horrible. What's so bad about having a 1 over r behavior? So suppose u goes to a constant. So phi goes to constant for r. What's so bad about this? So let's look back at the kinetic energy. T is equal to, the kinetic energy is going to be minus h squared d squared, so the energy is going to go like d squared over 2m d squared. But here's an important fact. D squared, the Laplacian of 1 over r. Well, it's easy to see what this is at a general point. At a general point, d squared is a term that looks like 1 over r, d squared r, r. So 1 over r, d squared r. D squared r times r on 1 over r. Well, r times 1 over r, that's just 1. And this is 0, right? So the gradient squared of 1 over r is 0. Except, can that possibly be true at r equals 0? No, because what's the second derivative at 0? As you approach the origin from any direction, the function is going like 1 over r, and so it's growing. But it's growing in every direction. So what's its first derivative at the origin? It's actually ill-defined, right? The first derivative is because it depends on the direction you come. The first direction in this way, the derivative looks like it's becoming this. From this direction, it's becoming this. It's actually badly divergent. So what's the second derivative? Well, the second derivative has to go as you go across this point, telling you how the first derivative changes. But it changes from plus infinity in this direction to plus infinity in this direction. That's badly singular. So this can't possibly be true, what I just wrote down here. And in fact, d squared on 1 over r, and this is a very good exercise for recitation, is equal to delta of r. It's 0. It's clearly 0 if r not equals 0, but at the origin, it's divergent, and it's divergent in exactly the way you need to get the delta function, okay? Which is pretty awesome. So what that tells us is that if we have a wave function that goes like 1 over r, then the energy contribution, energy acting on this wave function, gives us a delta function at the origin. So unless you have a potential which is a delta function at the origin, nothing will cancel this off. You can't possibly satisfy the energy eigenvalue equation. So u of r must go to 0 at r goes to 0. Because if it goes to a constant, any constant, we get a bad divergence in the energy. Yeah? If we calculate the energy, we'll discover that, that the energy is badly divergent if it does look divergent if we don't have u going to 0. So notice, by the way, as a side note, that since phi goes like phi is equal to u over r, that means that phi goes to a constant. This is good because what this is telling us is that the wave function, so true that u is vanishing, but the probability density, which is the wave function squared, doesn't have to vanish. That's about the derivative of u as you approach the origin from Tau. So this is the first general fact about central potentials. So the next one, and this is really the fun one, is that note, the energy depends on L, but not on N. Just explicitly, in the energy eigenvalue equation, we have the angular momentum showing up the effective potential, little L. But little m appears absolutely nowhere except in our choice of spherical harmonic. For any different m, this was pointed out before, for any different m, you would have the same equation. And that means that the energy eigenvalue can depend on L, but it can't depend on m. Right? So that means for each m, in the allowed possible values, L, L1 is 1, minus L, and this is 12 plus 1 possible values. For each of these m's, the energy is the same. And I'll call this E sub L because the energy can depend on L. Why? The degeneracy of E sub L is equal to 2 L. Why? Why do we have this degeneracy? Yeah, exactly. We get degeneracies when we have symmetries. Right? When we have a symmetry, we get a degeneracy. And so here we have a degeneracy, and this degeneracy isn't fixed by rotational invariance. And why is this the right thing? Rotational symmetry. So why did this give us this degeneracy? Well, what the rotational degeneracy is saying is, look, if you've got some totaling momentum, the energy can't possibly depend on whether most of it's in Z, or most of it's in X, or most of it's in Y. It can't possibly depend on that, but that's what M is telling you. M is telling you what fraction is contained in a particular direction. So rotational symmetry immediately tells you this, but there's a nice way to phrase this, which is the following. Look, what is rotational symmetry? Rotational symmetry is the same, but the energy doesn't care about rotations, and in particular, it must commute with Lx, and with Ly, and with Lz. Right? So this is rotational symmetry. And I'm going to interpret these in a nice way. So this guy tells me that I can find common eigenfunctions. And we're going to find a full common eigenbasis of E and Lz. Can I also find a common eigenbasis of E, Lz, and Ly? Are there common eigenvectors of E, Lz, and Ly? No, are there common eigenfunctions of Lz and Ly? No, they don't commute. Right? E commutes with each of these. Okay, so I'm just going to say, I'm going to pick a common eigenbasis of E and Lz. I could have picked Lx or I could have picked Ly. I'm just picking Lz because that's our convention. So notice, what are these two? Once I've chosen this, I'm going to work with a common eigenbasis of E and Lz. What are these two commutators telling me? These two commutators tell me that E commutes with Lx plus I Ly and Lx minus I Ly, L plus minus. Right? So this tells you that if you have an eigenfunction of E and you act with a raising operator, you get another eigenfunction of E. And thus we get our 12 plus 1 degeneracy because we can walk up and down the power using L plus and L minus. Cool? So this is a nice example that when you have a symmetry, you get a degeneracy and vice versa. Okay. So let's do some examples of using these central potentials. Yeah. It's 0. So E with Lx is 0. E with L, sorry, are you happy with that statement that E with Lx is 0? Yeah, good. Okay. So this is 0 because it's just Lx plus IOY. So E with Lx is 0 and E with Ly is 0. So E commutes with these guys. And so this is like the statement that L squared with L plus minus equals 0. Cool. Okay, so let's do some examples. So the first example is going to be, actually I'm going to skip the spherical well example, because it's just not that interesting, but it's in the notes and you really need to look at it. Oh hell, yes, I'm going to do it. Okay, so spherical well. So I'm going to do it in a bridged form, and maybe it's a good thing for recitation. Thank you, recitation later. So in the spherical well, what's the potential? So here's V of R. Not U bar and not UV effect, just V of R. Okay. And the potential is going to be this. So here's R equals 0. And if it's a spherical infinite well, then I'm going to say the potential is infinite outside of some distance L. Okay. And it's 0 inside. So what does this give us? Well, in order to solve the system, we know that the first thing we do is we separate out with YLMs, and then we rescale by 1 over R to get the function of U, and we get this equation, which is E on U is equal to squared upon 2m, the r squared, and plus the effective, well, plus L plus 1 over r squared with a 2m and an h bar squared. And the potential is 0 inside. So we can just write this. Okay. So this is, if you just, let me pull out the h bar squared over 2m. It's minus L plus 1 over r squared. Okay. So this is not a terrible differential equation, and one can do some good work to solve it. But it's a harder differential equation than I want to spend the time to study right now. So I'm just going to consider the case, special case, when there's zero angular momentum, L equals 0. Okay. So in the special case of L equals 0, E, and I should call this use of L, E use of 0 is equal to h bar squared upon 2m. And now this term is gone, the angular momentum barrier is gone, because there's no angular momentum, dr squared UL, which can be written succinctly as UL, or sorry, U0 prime. This is only a function of r. So now this is a ridiculously easy equation. We don't have to solve this equation. Right? This is saying that the energy, a constant times U, is two derivatives times this constant. So U0 can be written as a cosine of kx, or sorry, kr, plus b sine of kr, where h bar squared k squared on 2m equals e. And I should really call this e sub 0 because it could depend on L. Okay. So there's our momentary solution. However, we have to satisfy our boundary conditions, which is that it's going to vanish at the origin, but it's also going to vanish at the wall. So boundary conditions, u of 0 equals 0 tells us that a must be equal to 0, and u of L equals 0 tells us that, well, if this is 0, we've just got b, but sine of kr evaluated at L, which is sine of kl must be equal to 0. So kl must be 0 sine, must be n pi over, it must be equal to n pi, multiple of pi. And so this tells you what the energy is. So it's just like the 1D system. Right? It's just exactly like the 1D system. So now to finally close this off, what does this tell you that the eigenfunctions are? Let me do that here. So therefore, the wave function, fine.
So this would mean that if we've got our radius here,
So E0 of R theta phi. Oh God. This is so much easier to look at. So y sub E0 of R theta and phi is equal to y ln y0 m. But what must m be?
0.
0, because n goes from plus L to minus L. 0. I'm just not writing the arguments. Y0 0 times not u of r. It's times 1 over r times u. 1 over r times u of r. But u of r is a constant times sine of kr. Sine of kr, but k is equal to n pi over l. N pi over l r. Okay, and what's y0 0? It's a constant. And so there's an overall normalization constant, we'll call n. Okay. So we get that our wave function is 1 over r times sine of n pi over lr. So this is bad. There's a 1 over r. Why is this not bad? At the origin, why is this not something I should worry about?
0.
Yeah, because sine is linear, first of all, as determinant. So this goes like n pi over l times r. That r cancels the 1 over r. So near the origin, this goes like a constant. Yeah? So u has a 0, but the wave function doesn't. Cool? Okay, so this has a very nice, more general story for larger L, which, yeah, which I hope you see in the recitation. Okay, questions on the spherical well? So the whole point, yeah, go. That's true. That's it. So let me rephrase the question and tell me this is the same question. So this is strange. There's nothing special about the origin. So why do I have a 0 at the origin of my u? Is that the question? Okay, it's true. There's nothing special about the origin except for two things. one thing that's special about the origin is we're working in a system which has rotational symmetry. But rotational symmetry is rotational symmetry around some particular point. So there's always a special central point anytime you have rotational symmetry, so the point fixed by the rotations. So actually the origin is a special point here. Second, saying that little u has a 0 is not the same as saying that the wave function has a 0. Little u has a 0, but it gets multiplied by 1 over r. So the wave function, in fact, is not 0 there. So the physical thing is the probability distribution, which is the square of the wave function, and it doesn't have a 0 at the origin. That's fine? Okay, so the origin is special when you have a central potential. That's where the proton is, right? Right, okay. So there is something special about the origin. Wow, that was a really anti-Keplerian trademark. Okay, so that's what we're doing. So there is something special about the origin, and the wave function doesn't vanish there even if u does. It may vanish there, but it doesn't necessarily have to. And we'll see that in a minute. Other questions? Yeah?
So like, what are you
Good. The reason that u of r had vanished at the origin is that if it doesn't vanish at the origin, then the wave function diverges. Sorry, losing constant.
So where did I put this? U has to vanish. I'm just gonna put next to this.
Oh yeah, so this is like if the wave function, if u doesn't go to 0, if it goes to any constant, non-zero, then the wave function diverges, and if we calculate the energy, we get a delta function at the origin. So there's an infinite contribution of energy at the origin. That's not physical. So in order to get a sensible wave function with finite energies, we need to have the u vanishes because of the one. The reason that we said it had to vanish at L was because I was considering the spherical infinite well, where a particle is stuck inside a region of radius capital L, and that's just what I mean by saying I have an infinite potential. Cool. Yeah. Others. Okay. So with all that done, we can now do the hydrogen or the Coulomb potential. And I want to emphasize that we often use the following words when solving this problem. We will now solve the problem of hydrogen. This is false. I am not about to solve for you the problem of hydrogen. I am going to construct for you a nice toy model, which turned out to be an excellent first pass at explaining the properties observed in hydrogen gases, their emission spectra and their physics. This is a model. It is a bad model. It doesn't fit the data, but it's pretty good, and we'll be able to improve it later. Okay. So it is the solution of the Coulomb potential. And what I want to emphasize to you, I cannot say this strongly enough. Physics is a process of building models that do a good job of predicting. And the better the predictions, the better the model. But they're all wrong. Every single model you ever get from physics is wrong. There are just some that are less stupidly wrong. Some are a better approximation of the data. Okay, this is not hydrogen. This is going to be our first pass at hydrogen. It's the Coulomb potential. Okay, and the Coulomb potential, V of R, is equal to minus E squared over R. This is what you would get if you had a classical particle with infinite mass and charge plus E, and then another particle over here with mass little m and charge minus E, and you didn't pay too much attention to things like relativity or spin or lots of other things, and you have no background magnetic field or electric field and anything else, and if these are point particles and all of those things are false that I just said. But if all those things were true in that imaginary universe, this would be the salient problem to solve. So let's solve it. Now, are they all those things that I said that were false? The proton's a point particle, the proton is infinitely massive, there's no spin. Are those preposterously stupid? No, they're excellent approximations in a lot of situations. They're not crazy wrong. They're just not exactly correct. I want to keep this in your mind. These are going to be good models. They're not exactly. We're not solving hydrogen reason.
I've got a question. I'm just going to wait until, Mazavolt, basically my policy is I'm just going to try to wait until the lecture's done, then I'll address any questions.
Solve this idealized Coulomb potential problem. Okay, so let's solve it. So if V is minus E over R squared, then the equation for the rescaled wave function U becomes minus H bar squared upon 2m for U prime prime of R plus the effective tensor, which is H bar squared upon 2m L plus 1 over R squared minus E squared over R, U is equal to E sub LU. So there's the equation we want to solve. We've already used separation of variables, and we know that the wave function is this little u times 1 over r times yln for some l and some n. So the first thing we should do, anytime you're solving an interesting problem, the first thing you should do is do dimensional analysis. Okay? And if you do dimensional analysis, the units of E squared, well, this is easy. E squared must be an energy times a length. So this is an energy times a length. Also known as P squared L momentum squared over 2m, 2 times the mass times the length. It's useful to put things in terms of mass, momentum, and lengths because you can cancel them out. H bar has units of P times L. And what's the only other parameter we have? We have the mass, which has units of mass. Okay, and so from this, we can build two nice quantities. The first is we can build R naught. We can build something with units of a radius. And I'm going to choose the factors of 2 judiciously. H bar squared over 2m E squared. Whoops. E squared. So let's just make sure this has the right units. E squared has units of energy times the length, but H bar squared over 2m has units of P squared L squared over 2m, so that has units of energy times the length squared. So length squared over length, this has units of length, so this is good. So there's a parameter that has units of length, and from this, it's easy to see that we can build a characteristic energy by taking E squared and dividing it by this length scale. And so then the energy, which I'll call E naught, which is equal to E squared over R naught, is equal to 2m e to the fourth over H bar squared. Okay. So before we do anything else, without solving any problems, we immediately can do a couple of things. The first is, if you take the system and I ask you, look, what do you expect? This is a quantum mechanical, a 1D problem in quantum mechanics with a potential, and we know something about 1D quantum mechanical problems. I guess this guy. We know something about 1D quantum mechanical problems, which is that the ground state has what energy? Some finite energy. It doesn't have infinite negative energy. It's got some finite energy. What do you expect to be roughly the ground state energy of the system?
E naught.
Yeah, right. Roughly minus E naught. That seems like a pretty good guess. It's the only dimensionally sensible. Maybe we're off by factors of 2, but maybe that's, maybe it's minus E naught. So that's a good guess. A first thing, before we do any calculation. And if you actually take mu e to the fourth over h bar squared, this is off by, unfortunately, a factor of 4. This is equal to 4 times the binding energy, which is also called the Rydberg constant. Let me make sure I get my factors of 2 right. Yep, I'm off by a factor of 4. I'm off by a factor of 4 from what we'll call the Rydberg energy, which is 13.6 eV. And this is the observed binding energy of hydrogen. So before we do anything, before we solve any equation, we have a fabulous estimate of the binding energy of hydrogen, right? All the work we're about to do is going to be to deal with this factor of 4, right? Which, I mean, is important, but I just want to emphasize how much you get just from doing dimensional analysis. Immediately upon knowing the rules of quantum mechanics, knowing that this is the equation you should solve, without ever touching that equation, just dimensional analysis gives you this answer. Okay? Which is fabulous. So, with that motivation, let's solve this problem. Oh, by the way, what do you think R naught is a good approximation to? Well, it's a length scale. What? Yeah, it's probably something like the expectation value of the radius. Or maybe the radius squared, because the expectation value of the radius is probably 0. Okay, so let's solve this system. And at this point, I'm not going to actually solve out the differential equation in detail. I'm just going to tell you how the solution goes. Because solving it is a sort of involved undertaking. And so here's the first thing. So we look at this equation. So we have this differential equation, this guy. I want to solve it. So think back to the harmonic oscillator when we did the brute force method of solving the hydrogen system. Okay. When we did the brute force method, she sells seashells. When the brute force method of solving, what did we do? We did asymptotic analysis. We extracted the overall asymptotic form at infinity and at the origin. to get a nice regular differential equation that didn't have any funny singularities. And then we did a series approximation. Okay. Now, do most differential equations have a simple closed form expression, a solution? Not most differential equations have some, maybe if you're lucky, it's a special function that people have studied in detail. But most don't have a simple solution, like a Gaussian or a power law or something. Most of them just have some complicated solution. This is one of those miraculous differential equations where we can actually exactly write down the solution by doing a series approximation, having done asymptotic analysis. So let's, first off, so the first thing we'll do in dimensional analysis too, let's make everything dimensionless. Okay, and it's easy to see what the right thing to do is. Take R and make it dimensionless by pulling out a factor of rho, or of R naught. So I'll pick our new variable, it's going to be called rho, this is dimensionless. And the second thing is I want to take the energy, and I want to write it as minus E naught times some dimensionless energy epsilon. So these guys are my dimensionless variables. And when you go through and you do that, the equation you get is minus the rho squared plus L plus 1 over rho squared minus 1 over rho plus epsilon u is equal to 0. Okay, so the form of this differential equation is, okay, it's not different in any deep way, but it's a little bit easier. It's going to be the easier way to deal with this rather than to deal with any stupid constant. And so now let's do the brute force thing. Asymptotic analysis. And here I'm just going to write down the answers. And the reason is, first off, this is something you should either do in recitation or go through on your own, but this is just the mathematics of solving a differential equation. This is not the important part. So when rho goes to infinity, which terms dominate? Well, this is not terribly important. This is not terribly important. That term is going to dominate. And if we get that d rho squared plus u, rho goes to infinity, these two terms dominate. Well, two derivatives is a constant. You know what those solutions look like. They're exponentials, with the exponential being brute, with the power, the exponent, being brute epsilon. So u is going to go like e to the minus the square root epsilon rho. For normalizability, I picked the minus, I could have picked the plus, that would have been divergent. Okay. So as rho goes to 0, what happens? Well, as rho goes to 0, this is insignificant, and this totally dominates over this guy. On the other hand, if L is equal to 0, then this is the only term that survives. So we better make sure that that behaves gracefully. As rho goes to 0, asymptotic analysis is going to tell us that u goes like rho. Well, two derivatives, we pull down a rho squared, and so two derivatives in this guy, we pull down an L, then an L plus 1, so this should go like rho to the L plus 1. There's also another term. So in the same way that there were two solutions to this guy asymptotically, one growing, one decreasing, here there's another solution, which is rho to the minus L, that also does it, because we get minus L, then minus L minus 1, which gives us the plus L plus 1. But that is also badly divergent at the origin. It goes like 1 over 0 to the L. That's bad. So these are my solutions. So this tells us, having done this analysis, we should write that u is equal to rho to the L plus 1 times e to the minus root epsilon rho times some remaining function, which I'll call v, little v, little v of rho. And this asymptotically should go to a constant near the origin, and something that vanishes slower than an exponential at infinity. So then we take this and we do our series expansion. So we take that expression, we plug it in. At that point, all we're doing is a change of variables. We plug it in, and we get a resulting differential equation. Rho v prime plus 2 1 plus L minus root epsilon rho v prime plus 1 minus 2 root epsilon L plus 1 v equals 0. So this is the resulting difference equation for this little v guy. And we do a series expansion. V is equal to sum over sum from j equals 0 to infinity of a sub j, root of the j. Plug this guy in here, just like in the case of the harmonic oscillator equation, and get a series expansion. Now, okay, no, we wrote it out this way. Yes. And the series expansion has a solution, which is a sub j plus 1. This is actually kind of a fun process. So if you like quick little calculations, this is a sweet little calculation to take this expression, plug it in, and derive this recursion relation, which is root, or 2 root epsilon times j plus L plus 1 minus 1 over j plus 1. J plus 2L plus 2 AJ. So here's our series expansion. And in order for this to terminate, we must have that sum AJ max plus 1 is equal to 0. So one of these guys must eventually vanish. And the only thing that's changing is the little j. So what that tells us is that for some maximum value of little j, root 2 epsilon times j maximum plus L plus 1 is equal to minus 1. But that gives us a relationship between overall j max, little l, and the energy. And if you go through, what you discover is that the energy is equal to 1 over 4 n squared, where n is equal to j max plus L plus 1. And what this tells us is that the energy is labeled by an integer n and an integer L and an integer m. Right? These are from the spherical harmonics, and n came from the series expansion, and it's equal to minus E naught over 4 n squared, independent of L and m. And so by solving the differential equation exactly, which in this case we kind of amazingly can, what we discover is that the energy eigenvalues are indeed exactly 1/4 of E naught, and they're spaced with a 1 over n squared, which does two things. Not only does that explain, so let's think about the consequences of this very briefly. Not only does that explain the minus 13.6 eV, not only does that explain the binding energy of hydrogen as it is observed, but it does more. Remember at the very beginning, one of the experimental facts we wanted to explain about the universe was that the spectrum of light of hydrogen went like E naught over 4 n squared. This was the Rydberg relation. And now we see that explicitly. So we've solved for that expansion. But there's a real puzzle here. On very general grounds, we derived earlier that when you have a rotationally invariant potential, a central potential, every energy should be degenerate with degeneracy 2L plus 1. It can depend on L, but it must be independent of M. But here we've discovered, first off, we fit a nice bit of experimental data, but we've discovered the energy is in fact not just independent of M, but it's independent of L too. Why? What symmetry is explaining this extra degeneracy? We'll pick that up next time.
Okay, wow. This is something that, I mean, the broad strokes are similar to it, but I think there's some challenges because we're now working in spherical coordinates that I need to work on here. So I don't feel like, I'm just going to put some notes here. This was lecture 17. Definitely to review. Let me read. So I'm not going to pause here and go through it just because I think we're getting near the end. We're on 17, so I think it's probably better to just push forward and go forward with it. I think there's definitely some things that I'm finding a bit tricky just because some of this stuff, because of spherical coordinates, it's not seeming as obvious. This switch to U as opposed to R, this kind of thing is a little bit confusing. I probably will look at the explanations in this book. I found that helpful for the understanding that part. They didn't have it for everything, so it's possible that there is not going to be a description of this in that textbook. If there isn't, then I might try to find something somewhere else. Although again, it's tricky. I could try to look at the other session that has video lectures. So I could look at Barton's V-Box explanation, try to look at the lecture notes, try to look at some other materials to understand this. But again, I don't think I want to pause and do a second coverage right now. I think better to do some problem sets first, because that's going to clear up some issues that maybe are not as obvious right now. So I think I just want to go forward, lecture 18, but definitely have some work cut out for me. 18. I'm spelling 18 wrong here. All right. Maze Volt asked, could I live stream on what I think when starting a big ultralearning project? You could read the chat and give live solution. Well, I have. For this particular project, if you go to my first video, I do discuss sort of my overall thinking at the start. I mean, that's a little bit like I did kind of decide what I was going to do for this particular project. So it wasn't like I just come up with the idea of doing quantum mechanics or thinking of this particular project. So there is usually this kind of incubation period where I think about, well, I'd like to learn this subject. And then there's usually kind of thinking about, well, what would be the overall way of doing it? What would be the overall way of learning it? So I usually get some of those details before I'm actually, okay, I'm devoting a month to this, or I'm, working on that. Because obviously if I decided, let's say I decided to do a physics degree or something, that's going to be a very different kind of project than doing this. Or if I decided, well, I'm just going to read one short book about it, I don't need a month. I don't need to spend this amount of time. So the form that you're using, materials you're using, do in some senses define the project. So I do like to do that stuff a little bit before I come on camera and do these kind of things. If you have some questions about setting up projects, there's two things. One, if you Google my website right now, I probably won't look it up, but if you Google my website for how to start an ultralearning project, I do have a 2-article series where I talk about that. And even better, I have a book that's going to be coming out in August called Ultralearning, where I talk about these big ultralearning projects. So let's go forward to, let's go forward to the next one. Let me open up lecture 18.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. Or to view
Okay, so let me just quickly remind you of what we did last time. So unfortunately, today is going to be a little bit of what I wanted to do this time, and a little bit of what I would have wanted to have been done in recitation yesterday, because all recitations were canceled. So today's going to include a few steps along the way that I skipped over last time. Okay, so to review, from last time we talked about central potentials. The energy operator had a radial derivative term, an angular momentum term, and a potential term. So this would be true regardless of whether we were central or not. But if we have a central potential where this only depends on the magnitude of the radius vector, then we can use separation of variables and write an energy eigenstate as a radial part, which we will sneakily pull out a factor of 1 over the radius. As we saw last time, that was particularly convenient. It took care of this R and made everything nice and simple. So a radial part times a spherical harmonic. The reason we use a spherical harmonic is that neither of these two terms depend on the angular coordinates. The angular momentum, we know what its eigenfunctions are. So if we use a spherical harmonic, this angular momentum becomes just a constant. And having separated in this form and pulling out that sinky factor of 1 over r, the energy eigenvalue equation reduces to a simple 1D effective energy eigenvalue equation with a simple dr squared and an effective potential, where the effective potential is the original central potential plus an angular momentum term, often referred to as the angular momentum barrier, which is proportional to, you know, as Matt says, as Professor Evans says, in 804, one is forced to say h bar squared upon 2m repeatedly, and he pointed out that it would be much more efficient if I would just come up with a simple variable for saying it, or a sound. So I will attempt to henceforth call it. So the effective potential is L plus 1 upon r squared plus the central part of the potential. Props to Professor Evans. And this is true in general for central potential. The last thing we notice of this is that since the energy eigenvalue equation has been reduced to this form, which depends on L but is independent of M appears nowhere here, the energy can't possibly depend. The energy can't possibly depend on M, although it can depend on L. It's just E of L, and thus for every different value of M, I will get the same energy. Fixed L, different M. And there are how many values of M for fixed L? 12 plus 1. So the degeneracy of EL is 12 plus 1. Right? That's general for any central potential that only requires spherical symmetry. Okay. So then we study the example of the Coulomb potential, where the potential is minus E squared upon R. And we solved, or quickly reviewed, the solution of the energy eigenvalue equation. Yeah, okay, let me write it that way. Where R of what I will call, in place of E, I will simply write N, or NL of, is equal to E to the minus R over 2 R naught. N.
So let me just back up a second, because I think this is
how many
important.
values of M for fixed L? 12 plus 1.
So this is
degeneracy of E, potential is minus E squared upon R. And we solved, or quickly reviewed, the solution of the energy eigenvalue equation. Yeah, okay, let me write it that way. Where R of what I will call, in place of E, I will simply write N, R.
So this is magnitude R is equal to E over R negative E squared. So I want it to be. Let me just change this, because it should be the opposite direction. So let's just
NL of is equal to E to the minus R over 2 R naught. N times R over R naught.
I think we wrote this down already.
Times some simple function V sub N L of R over R naught.
You know, I'm going to write this down. I'm not sure they have this. Oops. R N L E minus. Get him to say it again.
is equal to e to the minus r over 2 r naught n times r over r naught to the L plus 1 times some simple function v sub n L of r over r naught, with the energy n Lm being equal to E naught, or I should say E Rydberg in our notation of last time, upon n squared minus bound state. So let's talk about this quickly. This term, the fact that it goes exponentially, falls exponentially large distances, came from the asymptotic analysis at r goes to infinity. And this is just saying it's a bound state. The probability density falls off exponentially as we go out to large radius. Yeah? This term came from the asymptotic analysis near r goes to 0. And near r goes to 0, the only term that matters is in the effective, this is 1 upon r, this is 1 over r squared, so this gets large more rapidly. This term is important, and that LL plus 1 gave us r to the L plus 1. We worked in dimensionless variables, rho, and here I replaced rho with r over r naught, where r naught was the characteristic scale we computed last time. And finally, this function v sub nl satisfied, again satisfied the energy eigenvalue equation, but having pulled out these factors such that asymptotically it's regular. So this function must be regular, smooth, no divergences, no poles, as r goes to infinity and to 0. Okay, and then we solved this by series expansion. And from termination of the series expansion, we got the energy. We got a relationship between the energy and L and M, and in particular, the relationship, this came from termination of the series, just like it did for the harmonic oscillator. And the termination of the series gave us that the energy was equal to minus a constant over n squared. Okay. With one additional condition, which was that n had to be greater than L. N had to be an integer greater than L, and L, of course, has to be greater than or equal to 0. So let me just quickly tell you how this arises, because this is an important fact about hydrogen, which I want you to understand. So the way that arises is we got the energy from a series expansion for this remaining function of r, v and L of r. And that series expansion started out by saying let v be of the form sum over j of a sub j, r over r naught, the dimensionless variable rho, to the jth power. So it's a power series. And when we plug this whole form together with this series expansion into that differential equation, we get just like we did before for harmonic oscillator, we get a set of relations between the various coefficients in that series, and we solve that by saying a sub j plus 1, by deriving a recursion relation, is equal to a sub j times 2 square root of epsilon. I'm going to have to be careful, j plus L plus 1. J plus L plus 1, yes, good, minus 1, upon j plus 1, j plus 2L plus 2. Okay. So, okay, fine, you get this recursion relation, looks absolutely awful. But it tells you that if you know A0, say is a constant, one second. If you know A0 is a constant, which is not 0, but if it's 0, then they're all 0, the function is identically 0. Because AJ plus 1 is AJ times the constant. So this had better not vanish, A sub 0. So the first term, the constant term doesn't vanish, which is good. It tells us V doesn't vanish, so we've already learned good. If V doesn't vanish, identically the origin, then we can determine A1 from A0 by multiplying by this. J is 0 in this, and L is whatever number we fix from while M. And so on, we can deduce all the higher A's and L's. It's a series expansion. This is the recursion relation for it. However, note the following thing. As J gets larger, so we go to higher and higher orders in the series. So we go higher and higher in the series, then J is much larger than whatever fixed number L is, and much larger than whatever fixed number 2 is. So this asymptotes to AJ times roughly 2 epsilon J upon J plus 1J. At very large J, this just goes to 2 epsilon over J. Now let's think about what that means. If I have that AJ plus 1 is roughly equal to AJ times root epsilon times 2 over J plus 1, I guess. Then this tells me that every time I increase J, I get a factor of J plus 1 and another factor of 2 to the epsilon. This tells me that A sub J is equal to A sub naught times 2 root epsilon to the J over J factorial. But those are the expansion coefficients. Of an exponential, right? Quantity to the n over n factorial. But that's bad, because if this series is the exponential series with argument 2 root epsilon, then this series becomes e to the 2 root epsilon r over r naught. But that's bad, because that would exactly swamp this term, right? That would defeat the asymptotic analysis we did at the beginning. If v is growing so large, twice as rapidly as this is divergent, or as is going to 0, then the net is diverging at infinity. That's bad. So in order for this to describe, for the series expansion to describe a good function that really does vanish at infinity, we need that this doesn't happen. So it must be true that J doesn't get large enough that the exponential in V overwhelms the decaying exponential from the asymptotic analysis. Ever cool that? So it has to terminate. But if it terminates, let's look at the coefficient here. If it terminates, this says that 2 root epsilon times J plus. If it terminates, that says that there's some J maximum. Well, let me write it over here. If it terminates, that means there's some value of J such that AJ plus 1 is 0. But if AJ plus 1 is 0, how can that possibly be? It must be that for that maximum value of J, the numerator vanishes. Specifically for that maximum value of J. Yeah? But what's the condition for that numerator to vanish for a specific value of J? I'll call J sub m or J max the maximum value such that A sub J max plus 1 vanishes. So J plus L plus 1 must be equal to 1. Or said differently, epsilon, which is the energy units of E naught, must be equal to 1 over 4 J max plus L plus 1, quantity squared. Cool? So that means that our solutions, our states, psi, are now labeled by 3 integers. They're labeled by L and by M from the spherical harmonic. They're also labeled by the value J max. Yeah? And J max can be any number from 0 to infinity. Right? Strictly it shouldn't be infinite, but any finite number, any integer. Because eventually the series terminates at J max. So it's labeled by these 3 numbers, and the energy is equal to of L, M, J max is equal to E naught minus over 4, and this E naught over 4 we already saw was E Rydberg 13.6 eV, times what value? Well, here's the energy units of E naught, Jm plus L plus 1, quantity squared. Where L is greater than or equal to 0, J sub n is greater than or equal to 0, and 1 is 1. Right? But this is sort of cumbersome. We can just as well call this quantity n, where n is greater than F. L as an integer. It can be equal to L, but it can be 1 greater than L or any greater integer. Is that cool? So instead of labeling it by Jm, the point at which it terminates, the series terminates, we'll label it by n, and you can deduce what Jm is by subtracting off L plus 1 from n. That tells you where the series terminates. Notice that this tells you something nice. This power series for V, if n is equal to L plus 1, has how many terms in it? So don't say that out loud, just think about it for a second. If n is equal to L plus 1, how many terms are there that are non-vanishing in the power series?
If n is equal to L plus 1, 0.
I will call you. Raise your hand when you have an answer. What's the value of J max if n is equal to L plus 1?
0.
So what term is the first one to vanish in the series? Okay, so how many terms are non-vanishing? Yeah, just the one, just the first term. So when when L is as large as it can possibly be, when L is equal to n minus 1, V is a constant function. It's just constant. When L is 1 less, when L is n minus 1, or n is L plus 2, then V has 2 terms in it, a constant and a linear. So the greater the difference between L and n, the more terms there are in the series. Okay? Cool. So anyway, this leads to this form of the energy. But as is usually the case, this sort of a brute force analysis doesn't give us a whole lot of insight into why we get the qualitative features we do. In particular, the qualitative feature that stands out most obviously to me, and to you guys, is the fact that the degeneracy is now much, much larger. In particular, we know from basic principles of essential potential, as we just reviewed, that any type of potential is symmetrically invariant. Symmetrically symmetric. It's spherically symmetric. Symmetrically symmetric. Any type of potential is spherically symmetric, rotationally invariant. There must be degeneracy of 2L plus 1 for every energy I use. There must be. Right? L can be 0. But if there's any angular momentum, then that degeneracy must be 2L plus 1. But this is much more degenerate. This is much more degenerate. And in fact, how degenerate is it? Well, the total degeneracy is, well, for any given En, the degeneracy is equal to, well, what are the possible values of L? So we have a sum, we have a state for every, we have some state for every given value of L. L can be equal to 0 if you go up to n minus 1, right? Because, again, n is some integer which could vanish L plus 1. So the smallest this can be is 0. So n can be L plus 1 or anything greater, i.e. L can go up to n minus 1, but it can't be any greater. Then for every value of L, there is a state m, there's a value of m which can be minus L all the way up to L, and it intercepts. So how many states are there? Well, there's one state for every value of n, L, and m. So it's this sum. The sum on m from minus L to L is 2L plus 1. So this is the sum, n minus 1, L equals 0, of 2L plus 1. And this is equal to, kind of beautifully, n squared. Just arithmetic series. So we have this huge degeneracy, which is much larger than 2L plus 1. It's a sum over 2L plus 1 from L to 0 to n minus 1. Where is this degeneracy coming from? Wow. Okay. So classically, or quantum-mechanically, we know the following. We learned the following. I hope it's under your fingernails at this point. That when you see a degeneracy, you should expect that degeneracy to follow from some symmetry. There's some symmetry of the system that is leading to a degeneracy by virtue of the fact that the generators of that symmetry, for example, for rotation, that's angular momentum, commute with the energy. And when you have an operator that commutes with the energy operator, as we've seen, you can generally construct new states given a single energy acting state by acting pseudolably with that operator. Yeah? So we should expect there to be some new symmetry. But it's very hard to see what symmetry means. Hydrogen is a central potential. It's just some stupid central potential. What's so special about the hydrogen system as opposed to, for example, the harmonic oscillator, which hopefully we will see in recitation at some point. The harmonic oscillator in 3 dimensions has degeneracy 2L plus 1. It's a central potential. It has to have degeneracy. Like 2L plus 1. But not n squared. Where did that come from? What's so special about the Kepler problem? So there must be some symmetry. It's not obvious what it is. But now let's use a note from classical mechanics. Noah's theorem tells us when we have a symmetry of a conserved quantity. We also saw this in the quantum mechanical version for expectation values. We have a conserved quantity. And in quantum mechanics, having a conserved quantity means that the energy commutes with some quantity. Because that controls the time evolution of the expectation value. So there must be some quantity, which I've written by an question mark, that commutes with the energy operator, specifically in the case of the harmonic oscillator. So what is that quantity? So actually, this quantity in classical mechanics was studied because the same thing is true in the Kepler case. In the Kepler case, the orbits close and they have their simple ellipses. They have all sorts of nice properties that beg for an explanation in terms of symmetry. And it was pointed out by a number of people, Laplace, Brunschlens, various people, that this is often called the Brunschlens vector, but I think you could blame it on any number of people, that there's a vector that in classical mechanics, for the Kepler problem or for the Coulomb problem, is conserved. And that quantity is P cross L, momentum cross angular momentum, minus m squared, m, e squared, and let me write m sub electrons, it's the mass rather than the quantum number, little m, e squared r vector. So it turns out this quantity is classically conserved, and if you make a quantum operator out of it, then E with A is
Runge, what was it called? I'm not sure what the to make this quantum mechanical.
Equal to 0. Was enormously not obvious. If it's obvious to you, you're a freak. Okay? It's really, really not obvious. You can go through and do the calculation. And when I say really not obvious, I mean, well, I'll show you what I mean in just a second. So you can go through and do the calculation. Classically, is this quantity conserved in the Kepler problem using Newton's law? The answer is yes. It's amazing. Quantum mechanics, they can do the same thing. Although I'm going to warn you for anyone who has the going to try, because I encourage you to, but it takes a little bit of brawn. Think about this operator for a second. Does this classical quantity have an obvious interpretation as a quantum operator? No, because L is R cross P. But now we have P, R, P. There's an ordering ambiguity. So you have to decide which order do you put that P in that R and the other P, and you P, P, R, R, P, R, P, R, R. Right? You write out which components you need. Presumably you need, for the Z component of A, you're going to get PX, LY, and LY, PX. But within that, how do you order the P's and the R's? because Ly contains dx, and in particular contains x. So there's no ordering ambiguity. So just be a little bit careful about this as a quantum mechanical operator if you do play with this. But if you do it and you're thoughtful about it, it's pretty easy to see that, look, it can be computed and checked that, in fact, the commutator vanishes. So at this point, it's tempting to say, there's an extra conserved quantity, we declare victory. The problem is, this didn't give us a symmetry. This just told us there's a conserved quantity. What's the symmetry behind this? What's the symmetry that ensures that this is a conserved quantity? It's obviously not rotations. It's something else. And so there are many answers to this question. One answer involves an explicit expression for in phase space, the change of variables, dx. And this is a variation that depends on, I'll write this as f of x and p. Okay, so there's a little vector parameter, and the change of the physical coordinates depends on both the coordinates and the momentum. This is a slightly strange thing, because it's like a change of variables where the position gets mapped into some nonlinear function of positions and momentum. That's a little bit weird, but you can do this. But I don't find that a terribly satisfying answer. And here's the answer I find most satisfying. It's not terribly useful for present purposes, but you're going to run into this again in 805 when you do what's called the operator method for the Coulomb potential, and it turns out to be an enormously useful machine. We're not going to use it in 804, but I want to advertise it for you. I want to give you a description, though, that isn't the description you're going to get in 805. The description is the following. 1935, guy named Fock, crazy guy, amazing physicist, played a huge role in the development of quantum field theory. I'm not exactly sure why he was thinking about this problem, but he was. And this was a very sort of Soviet thing to do at the time, I guess, to be hardcore and mathematical. So off he was going computing things, and he observed the following fact. How did he observe this again? Crazy long story. He observed the following fact. If you take the Kepler problem, and you work in momentum space, so write everything in terms of momentum, it turns out that the Kepler problem, or he referred to it as the Kepler problem, but I'll refer to it as the Coulomb problem, in 3D, three spatial dimensions. This is really crazy. Is exactly equivalent. There's a change of variables. It's kind of complicated. This is a projection. It turns out is exactly equivalent to the problem of a free particle.
Is this in momentum space?
In, wait for it, 4 dimensions, constrained to the surface of the sphere, to a 3D sphere. In the 4 dimensions. So you take a 3D sphere in 4 dimensions, you take a marble, you kick it, and make sure that it's stuck to the sphere. It will move in perfect circles, right? So obviously, it's moving on the sphere, it's just going to move in great circles. Okay, that's nice and simple. What's the symmetry group of that system? Well, the sphere is invariant under any rotation in 4 dimensions. SO4. There's a symmetry. SO4 is special orthogonal transformation. Special means it doesn't change length. Orthogonal means it's a rotation. So it's orthogonal rotations in 4 dimensions. And so now you can. So this should sound familiar because the angular momentum group, angular momentum in 3D, is SO3. It's rotations that don't change length in 3 dimensions. Okay, how many elements does this have? How many conserved quantities go along with this? Well, how many conserved quantities go along with rotations in 3 dimensions? What's conserved by virtue of rotational invariance in 3 dimensions? Angular momentum. How many components of angular momentum are there? 3. Great. There are 3. So it turns out that if you calculate in SO4, how many conserved quantities are there? There are 6. And when you do this mapping back down from the free particle in 4D, the Coulomb problem in 3D, 3 of them are the L's, and the other 3 of them are this A vector. Comes out spot on. So what it's telling you is that the spectrum of hydrogen, or at least the spectrum, I shouldn't say hydrogen, the spectrum of the Coulomb system, has an enhanced symmetry. It's the symmetry group of rotations in 4 dimensions. Why? I don't know, it's just kind of awesome, but I think that's about the best that can be said. It's true. So for certain very special potentials, we find that this sort of thing happens, and it happens in other systems too. You discover that there are accidental symmetries in your system. They shouldn't be referred to as accidental symmetries. They're inversely non-trivial functions of the rest of the system, and we're going to break this in a minute, and you'll see why we should refer to it as accidental. But in any case, the answer to the question, why do we have this giant degeneracy in the Coulomb problem, why is it n squared rather than 12 plus 1, is that there's an enhanced symmetry group. There's more symmetry than you would have thought. And there's a conserved quantity associated with it. And that conserved quantity corresponds mechanically to an operator that can use with the energy operator. Okay? Yeah. Indeed. Excellent. What do I mean in classical mechanics for quantity to be conserved? I mean that the time rate of change of that quantity under the classical dynamics, under classical evolution, is preserved. Right? So what's the quantum mechanical version of that? So the quantum mechanical version of that is, well, can we say that ddt of some operator, or of some observable A, is 0? Does this make sense? No, because this is, I mean, in the language we've been using, in the Schrödinger evolution description we've been using, this doesn't really make sense because it's an operator. That's not a quantity. The quantity is something you measure. So what do you measure? You measure the operator? In a state, you measure its expectation values. You might measure its eigenvalues, but the more general thing, it's expectation values. So this is something that depends on time because the wave function depends on time. Psi phi. Okay. So the best we can do to say something that's conserved is to say ddt of A is 0. But we've seen what the condition is for the expectation value to not change in time. In general, for any operator A, the time rate of change of its expectation value is the commutator of even A. I can't do the symbols good. Okay. So in particular, if this commutator vanishes, if the commutator vanishes equals 0, this is equal to sorry. Well, the wave function can be time varying, and I'm going to assume for the moment that the energy operator and the A operator are not themselves explicitly time dependent. Yeah, that's an important assumption. So let me just assume for simplicity that neither the energy nor the operator A that I'm looking at are explicitly time dependent. Like it shouldn't be like x plus TP. That would be annoying. So let me assume that that's not the case. You do have to deal with that sometimes. For example, if you are dealing with a system that changes in time, or like there's a background magnetic field or something like that that changes in time. But module that sort of detail. And also there's an IH bar. So where do the IH bars go? Do the units make sense here? AA, good. E and DDT. Whoops. So where do the units? Where do the IH bars go? Well, if you go on either side, you have to tell me if they go up or down. So, what is the Schrödinger equation? So there's, yeah, exactly, IH bar. Good, okay, good. So we need an IH bar. Man, okay. The spring has got to us all. So now, in the case that E with A is 0, imagine we have an operator A that gives equals 0, then DDT of the expectation value of A in any state is equal to 0. That's what I'll call conserved. So classically, to be a conserved quantity means that it's time dependent. Or mechanically, to be a conserved quantity means that it computes with the energy. Now, coming back to the question was, look, for angular momentum, there are only 2 numbers you can know at any moment in time. You can't know 3. You can know the total angular momentum, little l, and you can know the angular momentum in a particular direction, which we conventionally call z, little n, right? But you can't know some other angular momentum, like the angular momentum in x direction simultaneously. So what does it mean to say that there are 3 conserved quantities? I can't know 3 conserved quantities at the same time. They're not even well defined at some moment in time. The answer is there are 3 operators, Lx and Ly and Lz, all of which I would simply write as L vector, all of which can be with E. So while it's true that I can't take that systems don't have definite values of Lx, Ly, and Lz simultaneously, nonetheless, Lx, Ly, and Lz all commute with the energy operator, and as a consequence, the time expectation values are all 0 in this central potential. All right, so the time derivative expectation values are all 0. They're all constant. Yeah. You mean 1 over r? Yeah, 1 over r. So the question is, look, if you don't have 1 over r, do you get extra special things that happen for other potentials that aren't 1 over r with something else? It's not quite a unique case. So the question is, look, it's a very good question. So the question is this. This is a great question. Look, there's something peculiar about 1 over r classically. The orbits close. Right? You get ellipses. You don't get precessing ellipses. That's what you get. You have an anharmonic. You have no extra 1 over r to the 6th term or something, small correction, 1 over r long. Which we do in the real solar system. And so many body systems, instead of 2 body systems, so r orbit doesn't close. It's closed, but so that's special. And here we see that there's an enhanced symmetry. Are these things related to each other? So the answer is almost, in the following sense. For the harmonic oscillator, we also had a close, but there isn't a Rund's vector. Okay. However, the orbits close. So there's something special about that one too. Is there a conserved quantity there? And it seems like the answer to that is yes. There's an enhanced symmetry there as well. But it's not like this. It doesn't lead to this gigantic degeneracy. There's just extra structure that's nice about the harmonic oscillator. But for the harmonic oscillator, of course, it also closes. It's not this orbit, this. So there's a nice structure there, but it's not quite so simple. Okay. Yeah. One last question.
I was wondering if is it all correct definition of symmetry?
Yeah, it's not unrelated. I don't know how to make that connection sharp. The thing I can say sharp. So the question is, look, is that conserved quantity somehow related to the fact that there's equal time and equal area swept out equal time about points in the orbit? Which is the true thing about the coupler problem. And that's a good observation. I don't know how to make that connection, but it is true in the following sense: that both of those facts are guaranteed by the fact that you have closed orbits with a particular ratio, and that is indeed can be blamed on the conservation of the Rund's vector. I don't know how to make that connection direct and explicit, but indeed it is. So that's a fun question. I'll have to think about that. That's a good one. One of the totally awesome things about teaching it before is that every single time, so I'm asked a question I've never even thought of before. Forget never answered. Never thought of it. It's a great question. Okay. So everyone with the degeneracy. We have this gigantic degeneracy. So knowing what the degeneracy is and where it's coming from, at least more or less, is progress. But if you really understand why something is conserved, then you can break that conservation. You can break that degeneracy. So here's my question: is it possible? Can we, or indeed must we? Can we break or lift this degeneracy? So first, let me tell you what those words mean. So we have this gigantic degeneracy of the this guy. Okay, we have this gigantic degeneracy of the n squared of the Coulomb pedal. Can we break that degeneracy or lift it? So what do I mean by lift the degeneracy? What do you mean by lift the degeneracy is the following. Suppose I have a system that's degenerate. So it's got 2 energy eigenstates with the same energy eigenvalue. So this is energy. Then if I can kick the system in some way or modify it or bend it such that the energy levels are no longer degenerate, one state has been lifted above the other. And so we use the word to lift the degeneracy. Now you can see the 2 different states by measuring the energies. Is that cool? And It's also said to split a degeneracy or to break a degeneracy. So those are just words. So can we break or lift this degeneracy? Yeah. So sure, how do we break a degeneracy? How do we lift a degeneracy? We need to break the symmetry. Okay. So if we don't have the symmetry, we won't get the degeneracy. We've seen this before. So first off, let's think about symmetries that, what are the two symmetries that we want? Well, we got this degeneracy of 2l plus 1 from spherical symmetry, and we got this extra degeneracy of n squared from conservation of the Runge-Lenz vector. And conservation of the Runge-Lenz vector came from the fact that we had exactly the Coulomb system. So anything that is exactly the Coulomb system, but is still rotationally invariant, should still have the 2l plus 1 degeneracy, but not the n squared degeneracy. Cool? Like the harmonic oscillator, for example. So let's change the system. Let's find a small correction to the system that leaves it mostly the Coulomb problem, but with some small correction. So what comes to mind? So one good way to think about a physical, natural way to break this degeneracy, to break the symmetry, is to think about a real system that's described by the Coulomb potential. So the system that we usually talk about is hydrogen. Hydrogen is it's a proton, it's got a plus charge, it's got an electron, and it's attracted with a minus e squared 1r. Okay, so in hydrogen, is this the energy operator for hydrogen? Is this a good description of the energy operator for hydrogen? Well, that's a good start. But it's not exactly right, for a bunch of reasons. And in fact, in your first problem set, when you computed the time it takes for hydrogen classically to decay from the classical Borges, or from the classical, from the Borges, one of the things you discovered is that the electron starts out being non-relativistic, but very rapidly becomes relativistic. Right? Rapidly is like 10 times 15 seconds. This is a non-relativistic p squared upon 2m kinetic energy. That's probably not a perfect approximation. So let's ask, so the first example, example 1, is going to be relativistic corrections. Now, will relativistic corrections break rotational symmetry? They can't, right? Because relativity doesn't say this is the z direction. In fact, it does quite the opposite. Relativity, among other things, says don't get too hung up on what's the z direction. But relativistic corrections will not break the symmetry. So if we include relativistic corrections to the kinetic energy, this will change E. Change the energy operator, but it will preserve the rotational symmetry. E with L is equal to 0. So we won't break this rotational symmetry, so we'll preserve the 2l plus 1. So let's check to see that this is true. Okay. So to check to see that this is true, let's actually estimate out the correction to the energy due to the first non-trivial relativistic effect in the atom. The first non-trivial relativistic effect can be calculated all the way to the kinetic energy in special relativity of a particle of mass n. So that's easy. The total energy is the square root of p squared m squared c to the fourth plus p squared c squared minus mc squared. That's the rest energy. That's the total energy. So this is the kinetic energy. But this is equal to, well, if we pull out a factor of m squared c squared, this is m squared. MC squared times square root of 1 plus p squared over m squared c squared minus 1. And now if we Taylor expand this way,
I think that's p squared. I can't quite read it. Over m c squared. 1. I think that's right. Let me just let him write it again so I can hear what he's saying.
The factor of m squared c squared, this is m squared, m c squared times square root of 1 plus p squared over m squared c squared.
M squared c squared.
Minus 1. And now if we Taylor expand this guy, because if the velocity, or if the momentum is small compared to mc squared, or mc, I should say, if the momentum is small compared to mc, which is morally speaking at low velocities, the velocity is small compared to c, then this is 1 plus a small number. And we can Taylor expand this to get 1 plus 1/2 a small number. And the 1's will cancel, giving us only 1/2. So this is going to be equal to 1/2 that small number, p squared over mc squared, times m squared c squared times mc squared upstairs, giving us the first term, which is p squared upon 2m. That's the familiar classical kinetic energy. Rock on. What's the next correction? The next correction is the next term for this Taylor series, which is going to involve this quantity squared. So it's going to be p to the fourth over m to the fourth c to the fourth times mc to the fourth. The coefficient is a minus 1/8, so we have minus p to the fourth over 8 m cubed c squared. And that's down by a factor of m squared c squared from this guy and a p squared upstairs, which is what you get, p squared m squared over c squared, okay? So the correction to the kinetic energy for given momentum p is to correct it down by p to the fourth term. Everyone cool with that? Yeah. Because you, like Schrödinger, did problem set 1, and problem set 1 said, if you have an electron at the Bohr radius, classically, its velocity is about a 400th of the speed of light. 200th? something, it's small. It's a couple of order of magnitude smaller than the speed of light. So that number, that ratio there is 1 upon 200 or 400, I remember, squared. That's a very small number, so that's a reasonable approximation. Because what is the typical, that's an excellent question. So why am I talking about it as if the electron is sitting at that radius? And the answer is, well, look, what is the average momentum? What is the average value of p squared in, let's say, the ground state of the hydrogen atom? What's the average value of p? What must be the average value of p in the ground state of the hydrogen atom? 0 on 2 grounds. First off, p is a vector, and the ground state of hydrogen is gravitational invariant, doesn't break anything. Second, it's not going anywhere, right? It's a bound state, so it's just sitting there. It's got an average momentum 0. Carried momentum would be cruising. So it's got average momentum 0. Okay, fine, but what's the average momentum squared? What's the average of p squared? Well, we can actually do out that calculation. You're going to have to do that calculation on the problem set. And it's a small number, and it's in fact almost exactly what you guessed classically from the Bohr radius. So you have to know the h bar to compute the Bohr radius in the first place. So the answer is to the best of anyone's ability to define what's the momentum or the typical scale of momentum. That typical scale of momentum for the electron in the ground state of hydrogen is extraordinary. In fact, it's 100, 200, 400. Did that answer your question? It's a very good question. Okay, so here's the kinetic energy. And another way to say, by the way, another way to say that this approximation must be good is that we've already computed, ignoring the relativistic correction, we computed the ground state energy, and it was 13.6 eV, which is pretty good, since the binding energy of hydrogen is about 13.6 eV. So apparently that was a good approximation. And you might be disgusted by answer analysis like that, but that's what physics is, right? You write down such stupid calculating model that you know is wrong, but if it does a good job of fitting the data, you declare triumph and you call Stockholm. Okay. So, well, okay, it depends on the problem you've just solved approximately. So, okay, so here's the first correction. And so what this tells us is, therefore, the energy of hydrogen, or at least a better model of hydrogen, I'll call it hydrogen tilde, is equal to E Coulomb minus P to the 4th over 8, oops, that's an 8, M cubed C to the 4th. Oh, squared. Okay, wow, that's a deformed 8. Let's try it again. Much better. Okay, so this, however, is small compared to the kinetic energy because 13.6 is pretty close to 13.6. You'll notice I didn't include the rest of the significant digits. So this must be in the insignificant digits. So this must be small. So here's what I want to ask. We know that the energy of the Coulomb problem, NLM, is equal to E naught squared minus E naught squared over N squared, independent of L and M. What's the energy in this toy model of hydrogen that includes the first relativistic correction? Okay, NLN. Well, to answer that question, we have to resolve the Schrödinger or the energy eigenvalue equation, right? We have to refine the energy eigenstates. We have to solve that. And this is now going to be a much worse problem because it's going to involve a p to the 4th term, which is going to involve 4 derivatives. That sounds horrible, right? Can anyone think of a better way to just estimate the magnitude and the value of the leading correction from this quantity? Yeah.
Some variation on take an eigenvalue, plug it in, see what the error is, correct for that error, plug it again.
There's an iterative method for doing that. That's a very good guess, but there's an even easier way to estimate it. That's something we will call perturbation theory when we do this in 805, and doing that systematically is exactly the right answer. However, I want to do just the leading part of that. Yeah. Oh, dimensional analysis would be awesome. That's fantastic. So how would you compute P? Okay, so we didn't calculate P. So you can do a dimensional analysis and get a P because you have an E, you have an L, you can probably do it. But here's the problem with that, though. This is the correct first answer to any question of this kind. The correct first answer is plug in dimensional analysis and get an estimate for the order of magnitude. But we want more than the order of magnitude here. We're interested in splitting the degeneracy due to this interaction. So what that means is we want to see the different values of energies. What we care about is the L dependence that comes out of this correction. And we're not going to be able to get the L dependence from dimensional analysis because L is an integer, it is dimensionless. Yeah? So that will be the correct magnitude, and that is the first thing you do. What's the second thing you do? Yeah? Excellent. Let's just stick in the expectation value of p to the fourth. That's not exactly what I think to do, but if this is small, that's probably pretty reasonable. And what you'll find when you do it systematically using derivation theory, as was pointed out earlier, we can take the entire system, the entire energy eigenvalue equation. We can think of this 1 over m cubed c squared. We think that as a small number. And we can do perturbation theory in that small number. We can Taylor expand everything in that small number. And when you Taylor expand the exact equation, what you discover is the leading term in that Taylor expansion is the expectation value of p to the fourth over m cubed c squared. Okay, so this is a fantastic guess. Okay, good. So let's compute it. So E hydrogen is going to be equal to E NLM, which I'm just going to write as minus E naught. Okay, that's squared. Sorry, I wrote squared. Just E naught. If the energy equals the energy squared. At that point, every structural physicist goes up and lost themselves. Okay, so what is the correct answer here? So it's this quantity minus. So this is making it more tightly balanced. Notice the sign, because p to the fourth is strictly positive. P is real. So minus E naught over m squared. And if you go out and you do this expectation value, which I really should have put on the problem set, oh, I still can. It hasn't been posted yet, so it'll be posted this afternoon. I won't. I won't. It's not that bad, actually. Matt, what do you think? We'll discuss this afterwards. Okay, so which may or may not appear on your problem set. So if you do this calculation, what you find is the correction is E n squared, so E naught squared over n to the fourth. This time it really is n to the fourth, and now you have to worry about dimensional analysis. This is 2 energies, we want 1 energy, divided by, wait for it, mc squared, because it's a relativistic correction. That shouldn't be too surprising. Times the quantity 4n over, and here's where life gets awesome, L plus 1/2 minus 3. See, you laugh, but I feel delighted by this for so many reasons. So one is, that's beautiful. What a crazy combination of symbols. But the second and more important one is, look, it has an L in it, and the L is downstairs, right? That's good. It has more leverage that way. But so we've got this L up here. So now the energy depends on L. Good. We've broken the degeneracy. Different values of L give different energies. Yeah. So let's do that graphically. So in particular, what this tells us is that now, well, the Coulomb potential, the Coulomb energy commuted with the Lorentz vector, it must be true that the energy of this model of hydrogen, which includes the first relativistic correction, does not commute with the Lorentz vector. And indeed, if you check this, which is effortful but not intellectually difficult, indeed it doesn't vanish. And the failure of this conservation equation, the failure of this commutational relation to vanish, tells us that it's possible for the system to not be degenerate. And lo and behold, it is not degenerate. Okay? Yeah. Yes. No, sorry, I should have said that. There are other things that are important for relativity that we'll come to in a little bit. But this is, if you just look at kinetic energy, this is the first material correction. Yeah. We still have the 2L plus 1 degeneracy, exactly. Because does this correction violate rotational invariance? No, that piece word, that's a scalar on the rotation, it's just a number, not a vector. So, but E still commutes with L. Right? And you see that because this is independent of little n. Right? This is the mass of the electron. So this is independent of the quantum number little m. It only depends on the quantum number little L. So indeed, it is still degenerate. So let's go through this and see the degeneracy explicitly. And let me do that by drawing the following diagram. So what happens if we have the E1, or E1, which is the ground state? It has some energy, which is negative, which is minus E naught. Right? And when we include this first correction, what does it do? Well, it decreases it by some amount. Okay? Well, it doesn't change the number. It doesn't change the degeneracy because there's only one in the first place. Because L has to be 0 when n is 1. L has to be 1 less than n or smaller. And if n is 1, L has to be 0, which can't be smaller than 0. It's 0. It's just the one state. The degeneracy 2, 0 plus 1, which is 1. Okay, so that's fine. It just changes the ground state by some amount. Let's consider the second excited level. So in the second excited level, we have the states, and let me name this slightly differently. So this has energy minus E naught. The ground state had L equals 0.
Yeah, I'm going to write this down.
It had to. For the second excited state, n equals 2, how many states are there? 2 squared is 4. So there are 4 states. 2, 3, 4. And what are the values of L and M? Well, if n is 2.
So hold on a sec.
L can be either 0 or 1. If it's 0, then M has to be 0. If it's 1, M can be 1, or it can be 0, or it can be minus 1. Yeah? So this again is LM, LM, LM. So those are the 4 states with energy E2. In the hydrogen atom. And now, when we ask what are the energies of these 3 states, when we include this so-called fine structure, what is this going to do? Well, the ground state is going to get pushed down by some amount. Okay, I should draw this differently to make it more vivid. Okay. this gets pushed out by some amount with some value of L here to 0. But for these three states, which all have the same value of little l, 1, the denominator is larger. So the amount by which it gets pushed down is less. So these three states get pushed down less, but the same amount as each other. That cool? So these three states, degeneracy is 3, and this state degeneracy is 1. Now notice that 1 plus 3 is equal to 4, is equal to n squared. So these states split into multiplets, groups of states, which have to have the same energy by rotational invariance. If they have L equals 1, there must be 3 states with the same energy. There must be. And states with L equals 0, there's just the one state. Is that cool? And if we did the same thing for E3, let's just think about what happened. So here we have, I'm just going to write the L, I'm not going to include the M. We have the L equals 0 state times 1. We have the L equals 1 state times 3. And we have the L equals 2 state. And how many states are there in the L equals 2 state? Times 5. Good. And again, this gets pushed down to some value. This gets pushed down to some value. This gets pushed down to some value. Where this is 1, 3, and 5. And again, these add up to 9, which is 3 squared. So the degeneracy. So by turning on relativistic corrections, we break this degeneracy. We lift the degeneracy. We break the symmetry. You lift the degeneracy. Cool? Now, unfortunately, this isn't one we can control by turning the dial in the lab. No experiment that I can do in the lab will change the value of the speed of light or the, well, actually, there are experiments that will change the value of the speed of light. If you work in medium, right? If you work in medium, the effective speed of light is different, so that's going to change relativistic effects. So that's interesting. That tells you can actually vary this continuously if you can vary continuously the index of refraction of the ambient system. I invite you to think about how you might do that experimentally. It's a fun question. However, what I really like is something where Professor Evan in his lab can actually turn the dial and change the spectrum in a way that explicitly breaks the symmetry. Meanwhile, I also want an example that breaks the rotational invariance. I want to break the 2L plus 1 states up into 2L plus 1 states with different energies. I want to make them depend on the angular momentum of direction. What must I do in order to lift that degeneracy?
Rotational invariance.
Fantastic. You add a magnetic field. Why is that going to break the degeneracy? Yeah. Give me an answer that depends on not on your knowledge of chemistry, but give me an answer that depends on symmetries. Why does turning on a magnetic field have the potential to split the degeneracy into 12 plus 1 states? Thank you, exactly. You have no rotational symmetry, exactly. So that's pretty good. So let's break the 12 plus 1 by breaking rotational symmetry. There are many ways we can break rotational symmetry. We could turn on an electric field, we could turn on a magnetic field, we could, I'm going to put a shovel in the room, but anything that breaks rotational symmetry will do it, but a very convenient way to do it with magnetic field. Magnetic field is particularly beautiful. So this effect is now called the Zeeman effect. I believe it was Faraday, one of the classic electromagnetists of the 19th century, attempted to look at the spectral lines coming off glowing gas and see if they change by turning on an electric or magnetic field. It turns out to be a tricky experiment to do because you need to have a very well-controlled magnetic field, otherwise what you get is just a bunch of shmuts. So to get a clean spectrum, you have to have a very uniform magnetic field, which is not trivial. It has to be time independent. So Zeeman, at the very end of the 19th century, in fact, this experiment was done, I believe, in 96. So I think the paper came out in 97. But the experiment was done in 96. Zeeman did this experiment. He said, look, if I turn a magnetic field next to a hot glowing gas and lift the spectrum that comes off, anything happened. So why would you think that anything might happen? And the answer to this one is really quite nice. Look, if we compute the energy is going to be equal to the Coulomb energy plus a correction, which is the following. If you think of the atom as an electron carrying some angular momentum in the presence of the proton, right? If you think of the electron as a thing carrying some angular momentum and with a charge, if it has a charge and an angular momentum, it's going to have a magnetic moment, u. And the magnetic moment is going to be equal to the current of the charge times the area swept out divided by c, because we work with sensible units. And this is equal to minus, for the case of the atom, E-L over, man, I'm really dysfeasible. We write it here, minus mu, magnetic moment of the system dotted into the magnetic field that you turn on in the background. So this is a background magnetic field. I am turning on an electromagnet, which induces a magnetic field in some known direction with some known magnitude. Okay, so my dial is the magnitude of that B field. It can be larger, it can be small. And it's in a known direction. And the point is, our electron carries some, because it's orbiting, because it carries an angular momentum and it carries some charge, has some magnetic moment, so it behaves like a little bar magnet. And that bar magnet wants to anti-align with the background magnetic field that it's turned on. So there's an energy penalty to not being aligned. This is the usual dipole-dipole interaction from, or dipole potential from electrostatics. Okay, and mu here is equal to minus E over 2mc angular momentum. So this can be computed from a simple model of the atom. Whatever, it's easy to compute. So this is slightly annoying because B is in some arbitrary direction. Let's just simplify our life and say that it's E Coulomb minus mu B. And I want to turn on a magnetic field of known amplitude in a known direction. Let's call it the Z direction. So this is mu Z. Okay. But this mu Z, that's just mu Z is LZ times minus E over 2mc. So this is going to be plus E over 2mc BZ. I'm going to put this. It's all together, BZ. is telling you the velocity. The velocity is telling you the current, and then the area is the radius. So that's what's giving you the radius and the angular momentum. Okay. So this is our energy. What does this tell you about the energy eigenvalues? Yeah, they depend on n, right? And do we have to solve the energy eigenvalue equation again? No, because our energy eigenfunctions of EC are proportional to YLM, so they're already eigenfunctions of LZ. Ever go with that? So when I take this beast and I act on the wave functions I erased, but on the 1 upon little r, capital R, sub NL, Y sub LM, when I act on the YLMs, this is just going to give me H bar n, right? So this is just a constant when acting on the Coulomb energy eigenfunction. So this is a much easier problem. We don't even have to make any approximations. We can just say exactly energy Zenon is equal to minus E naught upon n squared NLM plus E H bar upon 2mc dz, the electromagnetic field, this is an m of electron mass, times little m. And I'm going to write little m sub L just to distinguish little m sub L from m sub E. Cool? So when we turn on the prediction here, when we turn on the magnetic field, a la Zeeman, our energy levels will get split according to the different values of n. Now, if instead of working with the pure Coulomb system, if we were in fact a little clever, and we'd already noticed that there's a fine structure, because they already knew that there was a fine structure at this point, they could see the different spectra in lines coming off of hot gas. So it's just an experimental fact, you can't turn off the fine structure. This is going to be equal to E and LM of our crushing the hydrogen atom with the fine structure corrected. So the L equals 1 states and the L equals 0 states are split. So let's focus, for example, on E2. So these guys have a different energy, the L equals 1 guys have a different energy than the L equals 1, the L equals 0 guys. What does this predict is going to happen? If I look at my spectral line. So what this predicts is the following. It says that, look, if you have some spectrum that looks like this. So this is a function of wavelength. This is a function of wavelength. And I'm looking literally at what comes off the prism. Right? I'm looking at the spectral line. And I'll have a line here, and these are going to be the L equals 0 states. This is n equals 2. L equals 0 states, and then there's the L equals 1 states. This is with zero magnetic field, B is equal to Z equals 0. If we turn on the magnetic field, dz not equals 0. What should we see? Well, what happens to this state? Nothing. It's the same thing because the m is strictly 0, so it's the same value. And this guy, what happens to it? The m equals 0 state is the same. But then it breaks up, as everyone said, it breaks up into 3 lines that are equally spaced. Yeah? It breaks up into 3 lines because one of them has m which is plus 1, one of them has m which is 0, one is m is minus 1. So the energies will increase or decrease. Let's say this is frequency. So we get this splitting, and another way to draw this is, as a function of b, let's draw the energy levels. So there's the 1, there's the 0, and this stays constant. And these guys, 1 is constant, 1 increases and 1 decreases. Ever go with that? When you start getting into strong magnetic fields, weird things happen, like these guys cross, and all sorts of subtle things can happen. But let's ignore the strong magnetic field case and just focus on this. So we see that these guys split. So this is what the Schrödinger theory, which came in where the full story would predict. It came a little bit after this, but well, this experiment was done in '96. So there's actually kind of an entertaining story about people trying to explain this effect classically. And you say, well, look, you have something going in the z direction, something going in the x direction, something going in the y direction. The part that has going in the x direction doesn't do anything. The z direction doesn't do anything. Part of the x and part of the y can have different polars. And there's a whole classical song and dance. It's crazy. It doesn't make any sense. But that's because they were trying to do classical mechanics to do quantum mechanics, which doesn't work. So I'm not even bother explaining what they were thinking. But anyway, so people came up with a sort of classical crush to say, well, that's not totally insane. So this is what Zenon got, for example, by looking at hydrogen. But he did more than just look at hydrogen. I can't remember exactly. I think he did it with sodium. Matt, do you remember? Sodium. I think he did sodium and iron. But anyway, but here's the funny thing that he got with sodium and iron. So this is a different experiment. Exactly the same setup, but he was looking at spectral lines in sodium. And the spectral lines in sodium did a very similar thing. There were some where 1 went to 1. And there were others where 1 went to... Why did we have 3 here? Just as a quick reminder, why did we have 3 states here? Because we had 3 states where L equals 1. This one state went to 1, 2, 3, 4 states. With none of them in the middle. And in fact, it's worse than that because they didn't go to equally spaced states in general. They generally did something slightly funny, and the beautiful plot in its paper looks like this. There are 4 states. And as you take the magnetic field to 0, these 4 states all coalesce exactly to this one state. So this one line is representing 4 different states. And this already included the following structure, so we know that this is all a single value of L. But that apparently has 4 states. That should worry you. What does that tell you about L? What does L have to be in order to have 4 states in your power? Have it in your field, what value? 3 halves. Crap. We already know that these wave functions are described by the YLMs, right? We solved that problem. We explicitly solved it. Here's the exact answer. It's the YLMs. But we've observed experimentally that L has to be 3 halves. But if L is 3 halves, YLM is equal to 0, because it's equal to minus itself. This is bad. This is 0. So this effect is called the Zeeman effect, and this effect is called the anomalous Zeeman effect.
Anomalous.
Which is strange for 2 reasons. The first reason it's strange is they show up in the same paper. And the second thing is, okay, you call it the Zeeman effect, is there some guy named Zeeman? Is there some guy named anomalous Zeeman? It's a very strange name. Anyway, so this was called the anomalous Zeeman effect, despite appearing in the same paper, because it's weird. It was deeply disconcerting to people. We now just call it the Zeeman effect, although we have a bad habit for entertainment value referring to it still as the anomalous Zeeman effect. I'm not the only one responsible for that bad habit. I'm going to point out that at the end of this paper, it's totally awesome paper, by the way, it's very readable, it's short. He says, I was looking at it last night, Zeeman says, quote, possibly the observed phenomenon will be regarded as nothing of any consequence. Okay, so a few years later, Pauli says the following. So Pauli says this actually, this is also totally lovely in Science from 1946. Pauli was in the U.S. during the war. After the war, he was at the Institute for Advanced Study. At the Institute for Advanced Study, he got the Nobel Prize, and he gave a little, for the exclusion principle, which we're about to get to, and he gave a little spiel, and it's written up in this edition of Science. And he says, quote, a colleague who met me strolling rather aimlessly in the beautiful streets of Copenhagen said to me in a friendly manner, you look very unhappy. Whereupon I responded fiercely, how can one look happy when he is thinking about the anomalous Zeeman effect? Okay. So this troubled people. Yeah. Yeah, he found all sorts of crazy states. So this isn't the only example, it's just the only one we can draw. But indeed, you can find 5 states, you can find states with 6. Oh, I didn't draw all the states. The spectrum is complicated and messy because it's so there's all sorts of crap. So I'm just not drawing. I'm just focusing on a specific set of spectral lines. Maybe the best way to draw that is. Okay. Okay. So this was really troubling. So let's put this on pause for a moment, and we'll go back to it in just a second. So meanwhile, there's something else that's sort of annoying about this system. We've got the Coulomb potential, and the Coulomb potential has the following beautiful property: the degeneracy of any energy state is equal to n squared. Meanwhile, various people were fond of observing the fact that that the number of states, which I'm looking at use of language called the degeneracy, of the level n in the periodic table is equal to, well, the first one there's 2, and then there's 8, and then there's 18. So 2, 6, or 2, 8, 8, 18, that's almost 2 n squared. Right? 2, 4, 8, 9, 18. Cool, maybe there's a relationship. Right? And meanwhile, it's very tempting to think that there's a relationship because imagine you have 4 electrons. If you have 4 electrons, what do you do? Well, you put an electron here, and then you can put an electron here, or you can put another electron here. You can put another electron here and here, or you can put them in any combination, 2 here, put 2 here, 2 here, 1, 1, you know, all sorts of stuff, right? But if for the moment you imagine that electrons have this funny property, imagine for the moment electrons have a property that can't be in the same state at once. And if you have 4 electrons, I don't know why, I'm desperate. I'm thinking about the anomalous Zeeman effect, so among other things, I have nothing better to do. So just for fun, let's imagine if I put an electron here, I can't put another one. So if I have a 2 electron atom, the second goes in one of these, a 3 electron atom, a 4 electron atom, and these guys are all related to each other because they live in the same energy level, but they have different L values, so they'll have slightly different properties. That suggests that the 1 L equals 0 state should be different from the 3 L equals 1 states, chemically. But wait, there aren't groupings of 2 or 1 and 3, they're groupings of 2 and 6. 2. Well, so Pauli, staring at this, in 25, said the following. He said, look, I'm going to conjecture 2 things. The first is that no 2 electrons can live in the same state, inhabit the same quantum state. That doesn't give us the periodic table, though. It gives us half the periodic table. There are twice as many states as you think. In hydrogen, as you think. And you might think that I'm being facetious, that he said something a little more sophisticated, but he really didn't. What he said is, I posit the existence of an additional quantum number, which the electron can have, which takes one of 2 values, which translated says, there are twice as many states as you think. Okay? So that's exactly what he said. So this is called the Pauli exclusion principle, and now this does a totally spectacular thing, and you've probably all seen this in high school chemistry or in college chemistry. Now, first electron goes here, second electron goes here, because there are twice as many states as you think, but you can't put another state in there because there's as many as you can have. One can go here, and you can put up to 6 in here. And that's it. So the E2 states, the n squared, which is 4 times 2 states, are somehow related to each other naturally. And this gives you the structure of the periodic table. And in fact, an awful lot of chemistry follows directly from this. So this is the Pauli exclusion principle. However, it's a little bit disappointing because, well, this is whatever, some ridiculous rule, but we're doing quantum mechanics and they're all ridiculous rules. On the other hand, this one is just stupid, right? This is just like, look, wouldn't it be nice? So in 25, a couple guys, really interesting characters, named Goldschmidt and Uhlenbeck. So Uhlenbeck, wow, we're really long time. Okay, so I'll just tell you this and then I'll get to the last of it later. So Goldschmidt and Uhlenbeck, who are young, kind of naive, they said, look, we've got two effects here. One effect is the anomalous-Zeeman effect. And there's this weird fact that states have the wrong total angular momentum. And we have the second thing, that there are twice as many states for an electron as you think in the Gould potential. How can these two things fit together naturally? Well, here's a guess. Suppose that the angular momentum that we calculated when we did the estimate of the breaking due to the Zeeman effect, suppose that angular momentum was not the right angular momentum. Maybe there's more angular momentum in the system. There's angular momentum in the system from the electron orbiting around, but maybe like a little tiny Earth, the electron itself can have some intrinsic angular momentum. It turns out Pauli had this idea before. In fact, Kramers had suggested this to him, and he was a very young guy at the time. And Pauli said, you're a believer in it, because if you calculate how small an electron has to be in order to fit all the other things we know, and you figure out how fast it has to rotate to explain the anomalous-Zeeman effect, the surface would have moving faster than the speed of light. That's ridiculous. Read my office. So then Uhlenbeck and Goldschmidt, I don't know, Goldschmidt, G-U-D. Anyway, these two guys write a paper and say, aha, well, we can explain this, but let's just not assume that this stupid thing is rotating. Let's just say an electron has some intrinsic angular momentum. I don't know. Why not? We'll have some electrons have intrinsic angular momentum, and if you assume that electrons have an intrinsic angular momentum, which I'll call S for the moment, so then the total angular momentum J is equal to L, is orbital angular momentum, plus some intrinsic angular momentum, which I don't remember what symbol they use, but we'll call it for the moment S, where this has the property that S squared for electron is equal to, the principal quantum number, don't call little s, is equal to 1/2, so M sub S is equal to plus or minus 1/2. Okay, so this is like the L equals 1/2 state, but it's not L, it's something intrinsic. It has nothing to do with anything rotating, it's just the fact about electrons. Suppose electrons have a little bit of spin. Then what you discover is, if you have the L equals 1 state and the electron has spin 1/2, what's the total angular momentum? 3 halves, right? So what do you get? You get quadruplets, like that. So this turns out to explain, if you include a small relativistic effect, this turns out to explain the anomalous-Zeeman effect. Bang on. Meanwhile, there was an experiment done in 1922, which was a Sturm-Gerlach experiment, which people discovered that people discovered that nickel, when sent through a magnetic field gradient, heads into one of 2 different spots. Never 3, never 0, always 2. How could that be? Electron spin. That wasn't realized until 1929 that the connection is there. So these guys came up with this ridiculous postulate. This was Uhlenbeck and Goldschmidt. And let me just quickly, U-H-L-E-N-B-E-C. Okay, so Uhlenbeck, amazing scientist, also the father of the mathematician Uhlenbeck, and she was a total badass and has inspired an awful lot of physics. Karen Uhlenbeck, who was at UT. So this is a pretty interesting, prolific guy, but he was also prolific in the following way. He ran a program at the Radial lab at MIT during World War II, and Goldschmidt worked with it. And when they were finishing up, when the war was ending, Goldschmidt became the scientific advisor to something called Project Alsos. Project Alsos was a project where the military went to the conquered territories in Germany to catch the German atomic scientists and bring them to a place called Farm Hall in England, where they listened to them, eavesdropped on them, Heisenberg, all the good guys, bad guys, all the great physicists in the German territory at the time who were deeply complicated people. And they listened to them in something called Farm Hall transcripts, or the transcripts of those recordings. They were written up in a book called The Epsilon Project, which is totally breathtaking and awesome. And Goldschmidt wrote a book called Alsos about this process of hunting down the German scientists. So Goldschmidt, U-D-S-M-I-T. I think, and he wrote a book called Alsos, which I heartily recommend to you because it's like a combination adventure story and beautiful bit of physics history. So these guys both they were both at MIT right during the World War, so there's a nice connection here. So these guys, fascinating characters, they came with this idea of some intrinsic angular momentum. Pauli then calls it spin. He uses the name. And he develops a mathematical theory of spin. And that mathematical theory of spin will lead to quantum field theory, relativistic quantum mechanics, and it will eventually lead to quantum computation, which will be at the top of the last week of our course. So what we've done so far is we've explained the discreteness of atomic spectra, and we've explained the structure of the periodic table. What we haven't done is we haven't explained why atoms form molecules or solids. And we also haven't explained what spin is at all. Those are going to be the topics of the next 3 weeks. See you next time.
Okay, so I went a little over today. Let me just switch over here. Yeah, so I went for almost 4 hours as opposed to my kind of pre-planned 3 hours, but I really wanted to finish this lecture so I can start on lecture 19 next day. Running a little low on paper here, so I'll have to get a new sheet here. So let me just write here, lecture 19. For the next class. So this means we got 5 lectures left, and there's obviously going to be a lot of work after these lectures are done. It's not going to be just as simple as just watching the lectures, then we've got it. If you have overheard some of this, it's quite complicated, as you can probably imagine. And so I'm going to have to do a lot of practice to master a lot of these things. So far, I would say that I'm keeping up pretty well with the high-level parts. I think, it's really the physics is in the details. That's kind of the expression here. And there's going to be a lot of details that I think I'm following, and then there's some kind of key insight that I'm missing. And so as I've been using this sort of metaphor of kind of a spiral for understanding of that, as opposed to just a staircase where you just sort of build on each layer and you go up, there's a kind of revisiting old ideas with the knowledge that you've gained from other things. So I try to use this kind of model. So this is my sort of first pass through this material, just as I did the first pass through lectures 1 to 10. And it's going to get deepened through doing those problem sets. And then after I've done kind of a full lap of the whole class, there's going to be a further process of sort of building on that, of trying to tighten things up that are kind of confused or that I didn't quite understand or that I want a better picture of. There's probably going to be a lot of things like that. And I'm going to just keep doing this as much as I can until we kind of get to the end, where I'm going to attempt this final exam, and we'll see how I do. I just realized when I was thinking about this how much notational specificity there is, meaning that they're using particular types of notation. There might also be particular types of problems that are being studied in this physics 1 that maybe aren't studied in quantum physics 1 of a different session. They may choose to study different things, and they may choose to emphasize certain things on the problem set that aren't on others. So that could create a problem. I don't really know so much for the physics classes. I know, for instance, when I did the intro chemistry class for MIT, they had sort of certain core problems were repeated, and then there were whole sections which were kind of like lecturer's choice of what they wanted to cover in the chemistry topic. So same thing with biology. And so what happened during the MIT challenge is that I was doing the chemistry class. There was no final exam. They had graded midterms for that class, and I did do those. But then there was the final exam, which I had taken from a different class. And of course, I don't like to look at the final exams before I do them. That kind of undermines the purpose of them. Doing the final exam, and I'm like, whoa, actually a lot of this material is not stuff from the session that I studied. So I have not looked at the final exam that I want to do at the end of this session. And now I'm recognizing that there might be that dependence. So hopefully that's not going to be too much of a problem. I'm going to go through this quantum physics textbook as well to work on some of these problems. That should give me a little bit of extra breadth. So I'm hoping that everything's going to be well, but I'm also recognizing that we might want to, we might be stuck, that might be an issue where I don't have solution sets to the problems that go for this class. So we're working on this method. We're working through the problem sets. We're going to work through maybe some problems here. But as always, I think the important thing is what you're learning, not really the evaluation method, not really the testing method. Testing and evaluation, of course, is a good benchmark to see how well you understood something. But how well you understand something is still an important idea, even irrespective of getting that feedback, getting that grade, or getting that mark. So we've got lecture 19, 20, 21, 22, 19, 20, 21, 22, 23, 24. So we've got 6 lectures left. Sorry, I said 5. We've got 6 lectures left to cover. Might be able to even finish by the end of tomorrow if we're going at roughly the pace that we've been going of about 3 a session. It may also overlap into Friday a little bit, depending on how quickly we can go through the next 6 lectures. And then the earlier we can start on problem sets, the better. I'm looking forward to getting back into problem sets. It's always good when you've been learning a lot of ideas. Okay, now it's actually time to practice it. So I appreciate everyone who's been following this. If you're watching this, I have no idea how many people are watching me right now, but if you're watching this a lot later, if you're watching this perhaps even years later, then yeah, well, I hope that this has been interesting, maybe just to see kind of my process for doing this, and maybe it's giving you some ideas for how you can study your own subjects. It's an exciting subject, it's a difficult subject, it's challenging, and maybe you'll also know the future outcome of how well we're going to do, and I'm anticipating these results. So I'm going to take a break for the day right now, and I'm going to be back on probably around sometime between 7:45 and 8 tomorrow morning.